when it comes to like switching, let's try to understand like what is switching and where do we need to perform the switching in our campus area network or the enterprise network. What topics we are going to cover in our switching content. So first, let's discuss about that. So the switching content that we are going to cover is going to be, this is going to be focusing on the CCNP CCIE switching part. So by the end of this content, all the topics from the CCIE switching will be done as well. So just to give you a brief idea, what topics, what content we are going to cover, let me show you. This is the content that we are going to cover from the switching part, right? So in the enterprise switching, what we are going to cover, this is the first point. This is the first topic for the CCIE Enterprise Infrastructure exam. So here in the network infrastructure, this is what we are going to talk about. We are going to talk about the Swiss campus. In the Swiss campus, we are going to talk about basic switch administration, where we will talk about managing the MAC address table, error disable recovery, layer 2 MTU. We'll talk about the layer 2 protocols such as CDP, LLDP, UDLD. Then we will talk about the VLAN, how to create the VLANs, what are the use cases of the VLANs and all. So we'll talk about the VLAN technologies, access port, trunk port, native VLAN, manual pruning, VLAN database and all, normal VLAN, extended VLAN, voice VLAN, and the VLAN trunking protocol, so that the VLAN information can be sent from one switch to another switch in an automated fashion, right? Then we will, once the VLAN part is done, VLAN and VTP part is done, then we will also talk about this DTP, dynamic trunking protocol, and we will talk about the STP. After STP, we will talk about the Ether channel. So in the Ether channel, in this Ether channel content, we have like layer 2 Ether channel, layer 3 Ether channel, using the protocol, manual, all the types of Ether channel link bundling that we can perform. We will talk about that, right? So Ether channel link bundling using LSEP, manual, layer 2 Ether channel, layer 3 Ether channel. What are the different load balancing algorithms in the Ether channel, and what happens when we misconfigure the Ether channel in the network, right? Then the spanning tree protocol. In the spanning tree protocol, we will talk about the STP and its variations. So STP, RSTP, MSTP, the variations, we will talk about that. So like whatever is the STP, what is RSTP, what is MSTP, we'll talk about all those variations as well, right? So this actually, from the content point of view, this is all that you need to know from the switching part. In the switched campus part, in the switched campus part, this is all that you should know, right? So we have like a basic switch administration, layer 2 protocol, VLAN. In the VLAN, we also have the VTP, DTP concept, trunking and all, then Ether channel, then this spanning tree, right? So in general, we have like these topics that we need to cover. Once this part is done, once this switched campus part is done, we will go to routing and everything is done, or if you have not covered the routing, we'll do it later on. SDA is done, SD-WAN will be done later on. This is done, this is done. So from the switching part, what else we are going to cover? From the switching part, we are going to cover this network security part. This network security part is going to feature the switch security, like how we can enforce the switch security in the network. That is going to be based on a VLAN access list, port-based access list, DHCP, snooping, dynamic ARP inspection, storm control, IP source guard, port security, private VLAN. Basically, the network security based in the network security, how we can ensure, how we can run variety of switch security features in the enterprise network, right? So all those switch security related features we are going to talk about here under the switching content as well, right? So under the switching content, we will talk about these switch security features as well, right? So in the switch security features, we will talk about this storm control, DHCP snooping, IP source guard, dynamic ARP inspection, port security, and everything. We'll talk about that, right? After that, we will also talk about, at the end, we will talk about this device management, where we will talk about the SNMP, where we will talk about the logging, how we can enable the SNMP on the devices, how can we enable the logging on the devices. We will talk about that as well, right? This is also part of the switching. And we will talk about this network services such as HSRP, VRRP, GLBP, DHCP, NTP, So this all is going to be covered in our switching curriculum. Anyone else is having any issues with the voice? Can you please confirm? Anyone else is having any issues with the voice? You guys can hear me properly, right? Is it audible properly? You guys can hear me? Okay. Okay. Siddiqui ji, you can rejoin once. Might be a little bit issue from the from the computer side, so you can rejoin once, because currently I am on full volume, so it should be audible properly. Right. So we'll talk about all these things. We'll talk about this switch security features and all these things, all these points. We will talk about that. Once it is done, once this part is done, once we are done with this security point, once we are done with the security, then we'll talk about this traffic capturing technique like span, rspan, yarspan, IOSXE debugging tools and all. So a little bit about the network operations at the very end. We will talk about them as well. We'll talk about like how the network operates and how network operations are going to work in that case. So all those things, like all those points we are going to discuss. All those points we are going to discuss from here in our switching content. So it is going to be a mix of, like, first we will talk about all the basic things, then we will talk about network services, then we will talk about network operations. So it will be a mix of all this content. So you have to keep a track, like you have to keep an eye on this content. This is the official CCIE enterprise infrastructure switching content that we have, right? So we are going to cover the things from here itself. So the switching part, you have to focus from this content, right? So we are going to start with section 1.1. This is going to be the campus. And once we are done with that, we will focus on the rest of the part, right? All right. So this is, let's begin with this content. Let's begin with this switching fundamental topic. Yes, actually routing part is already done. So this is the switching part. So once the switching part is done, we will most probably be starting the sd-wan, and then we will start the routing. So yes, I will be going through all the contents of the CCIE. So like, for example, you have already covered the SDA. Some people have already covered the routing part. So now we are focusing on the switching. So once the switching part is done, what we will do, either we will start this SD-WAN, or we will start this routing part again. So the cycle will keep repeating, and you will be able to complete all the things from the enterprise infrastructure point of view throughout the content. Right. All right. So let's start the switching part first of all. Let's start the switching part first of all. So we are going to focus on this switch the campus part first. We'll talk about how can we build switching campus, what are these switches, what are the models of the switches, what are different types of switches that we have in a modern day network. And since a few of you, or I think most of you people, have already gone through the software defined access class, so you know that they are planning on automating the configurations on the switches with the help of a controller called DNS Center. So you also know about that part. So now you will be able to relate all those things. You will be able to relate, like, what configurations we need to do manually and what configurations are actually pushed by the DNS Center in an automated fashion, right? So we'll be starting this campus part first of all. So first, what is switching? Like, in the switching fundamental, what is switching and where we can perform the switching in our enterprise network. So what is switching? Switching is like forwarding the frames based on the layer 2 address is what we refer to as switching. So when a device receives any particular frame and device decides to forward the frame based on destination MAC address, or layer 2 address. Layer 2 address is also referred to the MAC address. So forwarding of the frames based on the layer 2 address is known as switching. Forwarding of the packets based on the layer 3 address is what we refer to as routing. So forwarding of the frames based on layer 2 address is what we call as switching, and forwarding of the packets based on layer 3 address is what we call as routing. Why we are referring here as frame? Because because of the data link layer. At the data link layer, we call the data as frame. So typically a device that receives a frame and decides to forward that frame based on layer 2 address, this process is called switching. And whatever that device that can forward the frames based on the layer 2 address is what we call as the layer 2 device, such as a layer 2 switch. So any device that takes a frame on one of its interface and it decides to forward the frame out of the other interface based on the layer 2 address or the MAC address is what we call as the layer 2 device. And that layer 2 device is a generally used layer 2 device is what we call a switch. So switch is the most commonly used layer 2 device in our infrastructure. Now this term, the line between the layer 2 switches and the layer 3 switches is, it is going very thin. So modern day switches that we have in our campus area network, they are capable of performing the routing as well as switching in a campus area network. So almost all the modern day switch platforms that we have, except for a few, or almost all the modern day switch platforms that we have, these modern day switch platforms can actually perform both routing and switching. So to categorize a device, to categorize a switch based on if it is a layer 2 switch or if it is a layer 3 switch or if it is a multi-layer switch, that categorization is basically like, it is very hard to do in nowadays. In earlier days, in a traditional campus area network, in a traditional switching network, what we used to have a device referred to as a layer 2 switch. Layer 2 switch was a switch that decides to forward the frames based on layer 2 address only. Layer 2 switches that we had in our campus area network, they used to forward the traffic based on layer 2 address only. Then we have layer 3 switches. Layer 3 switches can do the packet forwarding based on layer 2 and layer 3 address, basically based on the MAC address and based on the IP address, right? So layer 3 switches, after like, some while, like they created these switches that can do the packet forwarding based on the layer 3 addresses as well. And in a modern day network, we also have these multi-layer switches, or typically referred to as like layer 4 switches, that can also include the port number in their packet forwarding decision. So traditionally, from the traditional network point of view, if we talk about, because we are going to talk about the traditional networking in our switching content, we are not going to talk about the software defined access, SDA, SD-WAN, or all those things. So in a traditional campus area network, you will notice that there are a few switches referred to as the layer 2 switches, there are a few switches referred to as the layer 3 switches, and there are a few switches referred to as the multi-layer switches. Now, layer 3 switches, people, they generally call layer 3 switches as a multi-layer switch, and it makes sense because typically a layer 3 switch works on 2 layers, layer 2 and layer 3. So it's like it is working on multiple layers. So people call that a multi-layer switch. However, the true definition of a multi-layer switch comes from this particular point, that a multi-layer switch can also take port numbers while deciding the packet forwarding. However, the layer 3 switch can just do routing. It cannot include the port number while deciding how to forward the data, right? Which gives us, in the multi-layer switching, which gives us a difference, that in a multi-layer switches, we can perform something called NAT, but we cannot perform netting on a layer 3 switches, because layer 3 switches, in a layer 3 switch, we do not actually have the capabilities to forward the frames, to forward the traffic based on the port numbers. Layer 3 switches cannot utilize those port numbers in their packet forwarding decision. So based on that, you can say that the layer 3 switches are different from the multi-layer switches, and that differentiation comes in the format of one of the most common difference that you will notice between the layer 3 switch and a multi-layer switch will come this NAT thing. NATing. Right. So, yes, port number means TCP UDP port numbers. Exactly. So, if I go on a layer 3 switch and I try to form netting, you can do that. If you have a layer 3 switch lying around in your campus network, in your organization somewhere, and just in case if it is free, you can try to go to any interface of that particular switch, and you can try to enable the netting and see what happens. Will we be able to facilitate the netting on the layer 3 switches? And if we are able to do that, can we really say that it is a layer 3 switch, or we are going to refer to as it a multi-layer switch? But anyway, in a traditional network, we can see commonly seen switches in a campus area network is a layer 2 switch, is a layer 3 switch, and a multi-layer switch. Layer 2 switches forward the frames based on the layer 2 address. Layer 3 switches can do the forwarding based on layer 2 and layer 3, both of the addresses. And the multi-layer switches can include the port numbers, TCP UDP port numbers, as well in the packet forwarding decision. Right? So forwarding of the frames based on layer 2 address is what we call as switching. And any device that forwards the frame based on the layer 2 address, they are known as the layer 2 device. And most commonly utilized layer 2 device is called a layer 2 switch. Remember, before the layer 2 switches, we had other things in the network as well, right? Before the switches came into the market, we have things like we have devices such as bridge, we have devices such as hub. We had devices to connect, like if we want to connect multiple devices all together, we can use the device called hub, and we can connect multiple devices together with the help of a hub, right? And if we have, for example, one hub there, one hub here, and we have a few devices connected here, and we want to connect these two segments, we can connect it via bridge. So bridge and hub, they were also the devices being used in earlier network. But nowadays, you will not see the use of hub, or you will not see the use of bridges in the network. In modern day network, there are two types of switches. One switches that you can manage, and one switches that you cannot manage. One switches that you can manage, and one switches that you cannot manage. So one are like, unmanageable switches, and one is called manageable switches. Unmanageable switches are basically like, for example, we have a D-Link switch or some other vendor switch that you cannot really manage using the console cable or anything like that, but you are not going to call it a hub. You are going to call it an unmanageable switch. That unmanageable switch that we have is just a typical network switch that we cannot manage. All the ports of that switch are going to be in up state. They are going to forward the data accordingly. So we cannot manage it. And the manageable switches that we have, for example, these Cisco Catalyst switches that we have, these Cisco Catalyst switches we can manage based on that console cable, telnet, SSH, and all those things. We can do variety of configurations on those switches. So we used to have the devices such as hub. We used to have devices such as bridge. We used to have devices in a modern day network. We have nowadays devices as switches. Switches, you can say, switches are successor to the bridges. Like switches came after the bridges in the market, and you will notice that a lot of things, for example, STP, spanning tree protocol. The spanning tree protocol was originally designed for the bridges, and later on, when the technology got updated to switches, that spanning tree protocol was implemented on the switches as well, right? So you will notice that in technologies such as STP, you will notice that the terminologies are still the same as bridge, like root bridge, like bridge protocol data unit, lowest cost to reach to the root bridge. So the term bridge and switch is synonymous in nowadays in a modern day network. That term bridge and switch is synonymous in a modern day network, but it was not so synonymous in older days, where we had a dedicated device referred to as bridge, and we had a dedicated device referred to as a switch. There are a few differences between a bridge and switch. For now, just understand that the switch is the device that we use in a modern day network, and bridge is more like a legacy device. It was a predecessor to these modern day campus switches, and switches are, you can say, like the successor of these old bridges that we used to have in the network. And before these switches came into the market, we also had the device called hub. We also had this device called hub. So we could have connected, like we can connect multiple devices together with the help of a hub, and we can connect multiple devices with the help of a switch as well. There are again some fundamental differences between the hub and the switch. So hub typically we do not use in a modern day network because of its drawbacks, because of its limitations, because of its disadvantages. So in a modern day network, we will use these devices called switches to build our campus area network. We can have manageable switches that we can manage with the help of the console cable, that we can manage with the help of telnet SSH. So any switch that gives us some level of manageability, like some level of management we can do on the switch, that switch is going to be referred to as, the manageable switch. But if the switch is not giving you any option to manage it, that switch is you are just getting the option to maybe monitor it, but you're not getting any option to configure that particular switch. That switch is typically referred to as an unmanageable switch. And typically in an unmanageable switch category, you will see like companies such as D-Link or even Cisco also. Cisco also creates a few like unmanageable switches that you can install in a small branch, and you can take the benefits of the same. It looks like this. Like, so for example, this is some unmanageable switch that you can purchase from Cisco, from D-Link. You will not be able to manage it. There are a few ports here that you can use to connect your network devices. There are a few uplink ports here that you can use to connect to the other D-Link switches, right? So, but there will not be any option to configure any, for example, VLANs or any other things onto these particular ports, right? So this is typically an unmanageable switch that you can purchase and you can install in your network. If you're not too much worried about the management of the network, you can always go for these unmanageable switches. And these unmanageable switches are offered by Cisco as well. So just in case, if you are willing to go, or if you are willing to purchase the Cisco unmanageable switches for small businesses, you can also purchase them as well, right? These are not manageable. All right. Now, we have different types of switches. Since we are talking about it, let's see what type of switch products Cisco offers, right? So let's see how many types of, or what type of products, switch products actually Cisco is going to offer. So if I search, for example, Cisco switch products, and I click on this first link, I will see all the platforms, all the models that the switch offers, that the switch has, that Cisco has in its portfolio when it comes to switches. So in switches, in Cisco portfolio, we have like these types of switches, like blade switches, campus local area network switches, campus local area network switches, campus local area network switches, data center switches, industrial Ethernet switches, LAN network management switches, LAN switches, service provider switches, switches for virtual networking and all. So these are all the categories that Cisco offers the switch products in, right? So for example, if we are going to, and if you notice here, you will notice that modern day campus area network, modern day campus area network, modern day local area campus local area network, modern day campus local area network is all about Catalyst 9000 series switches. Modern day campus local area network is all about the Catalyst 9000 series switches. We can also have the Catalyst 3000 or 6000 series switches in some campus area network, but the modern day campus area network is all about the Catalyst 9000 series switches. See, Catalyst 9400, 9300, 9200, 9600, 9500. So modern day campus area network, modern day campus local area network is all about these Catalyst 9000 series platform. And you should not be very confused with the 9000 series switches with 2000 or 3000 series switches, because eventually these offer the same capability that we used to get in Catalyst 2000 series switches. These offer the same capabilities that we used to have in Catalyst 3000 switches. These offer the same capability that we used to have in Catalyst 4000 series switches, such as 4565, with some enhancements as well, of course, with some enhancements as well. Right. So you are not going to say that it is a layer 2 switch, it is a layer 3 switch, it is a multi-layer switch. You are not going to say that. But if you want to relate it, if you are going to relate the functionalities that we used to get in a Catalyst 2000 series switches, such as 2950, 2960, if you want to relate like what switches in a modern day campus network are equivalent to 3550, 3560, 3750, 3738 and all, what switches are equivalent to these 4000, 45, 46, 45, 48, 100 series switch platforms. So typically you will notice that whatever facilities are offered by these Catalyst 9200 series switches, all the facilities were there in Catalyst 2950, 2960, these Catalyst 2000 series switches in an older platform. These Catalyst 9300 series switch platforms, they offer the same capability that we had in Catalyst 3000 series switch platform. So almost equivalent with some enhancements. What enhancements? For example, all these switches can be managed via centralized controller called a DNA center. And your 2950, 2960 cannot be, like, you cannot do it in those actually. So modern day campus local area network, in a modern day campus local area network, to build a modern day campus local area network, you will see that they typically use these Catalyst 9000 series switches. So if I, let's say, for example, want to know in detail about the Catalyst 9200 series switches, I'm just going to click on that and I can refer to the data sheet for this Catalyst 9200 series switch platform, right? You can read about it. What are the models like 9200 series switches, like 9200 24 PB, 48 PB, PXG, and different actually models are there. You can just refer to these models that they offer. And if you want to know about in more detail, you can go for the data sheet of that particular switch, where you will get all the information in very detail. If you want to compare it, you can just click on compare, and you can compare between the switches respectively as well. And you can see based on your requirement, like for example, you want to compare 9200 series switches with 9200 switches, you can also compare between those two switches and their facilities accordingly. Right. So if you want to get the information in very detail about a particular switch, you can always go for data sheet. You can visit this website, this Cisco website, just in case if you are going to purchase a Cisco Catalyst switch, you can always visit this website and you can refer to a variety of resources that you have available for these Catalyst 9200 series platforms, right? So for example, data sheet and all, if you want to get the information, you can get the information from there as well. Everything is well documented and you can get all the information from here. Or you can just search Catalyst 9200 series, Cisco Catalyst 9200 series switches, and you can just search for the data sheet. Here, you can just search data sheet and it will just show you, it will give you this data sheet. And here you can refer to this data sheet to get more detail about that particular switch, right? So for example, you can get the product overview, you can get the features, whatever features are offered by those Catalyst 9200 series switch platforms. So different models that we have, what features are offered by those different models, you can go for that. You can check for like performance and scalability, right? How many routes, for example, it can handle. Now, if it says that it can handle 4000 number of routes, how can I categorize this particular switch in a layer 2 switch category? If it says that it can handle like 4000 number of routes, it can handle 2000 number of IPv6 route, it can in fact handle 1000 number of multi-layer multicast routing as well, ACLs, quality of service. So how can I categorize this Catalyst 9200 series switch as a layer 2 switch? In fact, we cannot categorize this 9200 series switch with the layer 2 switches. So this supports routing. See, this supports the routing. What software it runs? It runs on iOS XE. What are the facilities available on this particular software? You can get all that, right? You can also take the benefits of software-defined access on this Catalyst 9200 series platform. You can also manage this particular switch based on the like web user interface as well. You can also perform routing here. If you can run protocols such as RIP version 1, RIP version 2, RIP-NG, OSPF, if you can run all these protocols, EIGRP, IPv6, ISIS, if you PIM, you can also run multicast routing, you can also run IPv6. If you can perform routing on this Catalyst switch platform, then how can you categorize, or how can you put this switch in a layer 2 switch category? So we cannot actually. So like I said, this point in the modern day campus area network, it doesn't make that much sense. Like in the modern day campus area network, this concept of layer 2 switch, layer 3 switch, and multi-layer switch is almost going away. Like we will very rarely see layer 2 switch being used in a campus area network. At the access layer, we might see at most, like we can see like 3850 series switches, or 37, we can see like layer 3 switches being used in the campus area network. And if you have covered the SDA, and if you remember the SDA classes, you will notice that they recommend having the routed access layer. What do we mean by that? What do we mean by this routed access layer? They recommend that in between your access layer switches and the distribution layer switches, you also perform the routing. They want you to create the network in such a way that routing is enabled in the entire campus. And if you want to enable the routing in the entire campus, you cannot connect a layer 2 switch on this particular access layer. So these categories, layer 2 switches, layer 3 switches, multi-layer switches, you might not. I'm not saying that layer 2 switches are completely obsolete. I'm not saying that. In your campus area network, you might still be using the layer 2 switches. You might still be using Catalyst 2950 series switch platform, which is one of the most widely utilized layer 2 switch in a campus area network. Or you can also use 2960. However, it does support some routing functions such as OSPF. So typically people do not call it a layer 2 switch, but yeah, you can also go for this 2960 series switch platform. But you will notice that Cisco has already announced end of sale, end of license for these different switch platforms. And if you want to purchase a new Catalyst switch in a modern day campus area network, at the end, it is all going to be like Catalyst 9000 series switches. So based on your requirement, you are going to go to this data sheet and you are going to refer to the data sheet of these different switches. And based on the data sheet, you are going to observe which switch is going to be perfect for your infrastructure. Where exactly you are going to add that particular switch? Are you going to add that switch as something called access layer? Are you going to add that switch as something called core layer or distribution layer? Are you going to add that switch in a data center infrastructure where we use the Nexus series switches running on the NXOS operating system? Are you going to add on the switches in the industrial Ethernet? Right? So based on where exactly you are going to, are you going to run the switches are you going to configure the switches in a service provider environment? Metro Ethernet series switch platforms we also have. For the small businesses, we also have. For the small businesses, we also have these some unmanageable switches, some manageable switches as well. Maybe you are not even following the access layer, distribution layer, and core layer concept. You just have a connection from a service provider, and that connection got terminated on a simple router, and we have a very small switch, and this switch is going to connect to 10 devices. We are not even following that core distribution or access concept. So based on the requirements, based on your requirement, you are going to refer to these switch products, and based on your requirements, you are going to purchase one and install it in your campus area network. For more details, if you want, you can always refer to the data sheet. You can always refer to the data sheet of these switches, always refer to the documentation of these switches. You can always see the documentation, resources, and everything. And since it is all well documented, you can decide based on the, for example, bandwidth available, based on, for example, ports available, based on, for example, can that switch be managed via DNS center or not? So based on all those things, you can decide that, okay, which switch you might want to use in your campus area network, right? So modern day switches platforms are these 9,000 series switches. We do have like we were using 3850. We are still using 3850 in our lab environment. So we still have like Catalyst 3000, 6000 series switches, but in the modern day network, most of the switch platforms that we will see are these Catalyst 9000 series switches. And the biggest advantage of these Catalyst 9000 switches are the capability to be managed by a centralized controller called DNA center. One of the major advantage of these switches is the ability to be managed by a controller called DNA center, which gives us the software defined capability in a campus area network as well. And most of these switches that we have in a modern day campus area network, they are routing capable. So we cannot actually categorize that switch just as a layer 2 switch. That switch can perform switching, that switch can perform routing, and some of those switches can also perform netting. So those switches are going to be more like categorized as a multi-layer switch instead of just categorizing them as a layer 2 switch. Layer 2 switches are those switches that can take their forwarding decision based on layer 2 address only, that is MAC address. Layer 3 switches can do that decision, can take that decision based on layer 2 and layer 3, both the addresses, means MAC and IP. And the multi-layer switches that we have, multi-layer switches are going to do that based on the layer 2 address, layer 3 address, and the layer 4 address, which is the port number, TCP UDP port number, that one. So nowadays, since most of the switch platforms are routing capable, so this is not going to be that much applicable in a modern day network. But hey, in the traditional campus area network, you will notice that this concept of layer 2 switches, layer 3 switches, this multi-layer switches is still applicable. Right? Any doubts so far? Anyone? Let me know. Any questions? These are the switches that we typically see in a modern day, like in a campus area network. In a modern day campus area network, we see the switches like 9200, 93, 94, 95, 96. When it comes to Catalyst 3000 series switches, we have 3650, 3850. Actually, these switches can be managed via DNA center, so they are still there. But rest of the switches such as 3750, 29, 26, like those are no longer there. Catalyst 4500 series switch platform, 65, 68, Catalyst 9800 series with the embedded WLC. These are some switch platforms that you will notice in a modern campus area network. Now you cannot actually categorize it. You cannot categorize like out of all these switches, what switches are layer 2 switches, what are L3 switches, and what switches are multi-layer. Because almost all these switches, like, or not almost, actually, all these switches can perform the routing. So if they can perform the routing, they are going to be a layer 3 switch. Some of these switches can also have that netting capabilities. So they are going to be referred to as multi-layer switches. You can refer to the data sheet for the details, like out of these switch categories, what switches support netting, what switches does not support netting, what switches support routing, what switches does not support routing. You can always refer to that information from the data sheet. Right? So any questions so far? Anyone? Let me know. Any doubts? All like that. Now, let's say we have purchased the Catalyst 9300 series switch, and we have installed that Catalyst 9300 series switch in our campus area network. We also have connected a few devices onto this Catalyst 9300 series switch, and that 9300 series is also connected with other switches in our campus area network. Now, these Catalyst 9300 series switches, or any switch, not only these, any switch that you see in this PPT, in this slide, any switch that you see here, these switches are going to have these ports where we can connect our end users. Yes, Raj, let me know.
When we discuss about the this 9K switches, and we say it comes with the DNAC license. So for the DNAC, do we need a separate kind of license from Cisco, or it comes default with the iOS XE?
Actually, see, as per my experience, what I have faced actually. So let's say you are going to purchase. Let's talk about since let's talk about the license. Since you know that part is also not covered in our DNA. Let's talk about the licensing for a moment. Okay. So when it comes to licensing part, like all these catalyst switches that we have, these like 9200, 9300, these switches are capable enough to be managed via the DNA Center appliance. The DNA Center appliance is a centralized controller from where we can manage all these switches, but it will require some licenses for the same. So when it comes to the licenses on these catalyst switches specifically, we have two types of licenses. We have two things. We have one license that what we call perpetual license, or that is the base license. The base license or perpetual license, that license allows us to use the basic functionalities of the switches, such as switching functions and everything, right? That base license is like IP based license and other different types of licenses that we had. Now those licenses got changed into this this here: network essential, network advantage. Network essential, network advantage. This is the base license. This is the perpetual license that we have to install onto the switches so that those switches can get functional, right? So let's say we are not going to manage the switches with the DNA Center. Forget about it for the moment. Forget about it. So this is the license, or this is the license that runs as the base license, on these switches. So if you have like a network essential license onto your switches, what capabilities you will get? You will get these capabilities, You will get like essential switch capabilities, layer 3 routed access, programmability using the netconf, restconf, and all those things. You get the option for zero touch provisioning. You get encryption. You get like span, rspan. You get all these things, right? But you do not get all the facilities. If you want to utilize all the facilities, you must go with the network advantage license. License is going to be part of the purchase. So if you are going to purchase the switch, you have to specify the license there. So let's say if I go with the network advantage license, we get additional these things. We get like full layer 3 routing functionality. We can use VRF, VXLAN, Lisp, and everything. We get the high HA functions, high availability, non-stop forwarding and everything. We get like manual operations through the CLI or through the web UI. Automation through the DNA Center is not supported in this one, right? Apart from that, we get advanced multicast to 56-bit MACsec encryption. So these are the options that we get if we go for this network advantage license. So we have two options. Either we go for the network essential or we go for the network advantage license. And these are called the base license or perpetual license. These are the base license that you have to have, on the switches so that the functionalities of the switches can be enabled. And if you want to manage that switch via DNA Center, you need DNA advantage or DNA essential license. Remember, if you have network essential license as the base license, you have to go with the DNA essential. And if you have the network advantage as the base license, you have to go with the Cisco advantage license, right? So you might think that it is optional. You might think that it is optional, that, okay, if it is required, then I will go for this DNA license or I will not. But in fact, actually, while doing the order, you have to add the licenses for the DNA. It is mandatory they have made it mandatory for you to purchase the DNA license at the time of switch purchase itself. You cannot purchase the switch without the DNA license. And if you, for example, are not going to use the DNA center in your campus area network, you can just go with the basic, like, DNA essential license, this basic thing. It will include like all those things. It will include all those things that we have in this traditional licensing. Like it will include all those things. Additionally, like even though you don't want to manage it via DNA center, but additionally you can do like these things via the DNA center. Right? For example, you can do things such as LAN automation. You get the overall health dashboard. You can do the PNP, wide area, Cisco wide area Bonjour, flexible net flow, embedded event manager, software. These are some functionalities that you get in addition to the basic ones in this Cisco DNA Essential license. And if you want to use a full-fledged DNA center in your campus area network, you have to go with the DNA Advantage license. And this DNA Advantage license is going to include everything. It is going to include everything from the SDA point of view. And if you are focused on, or if your network is focused on a cloud, like, you have cloud delivered applications and all, you can also go for this DNA Premier license. And the DNA Premier license, if you go, you get additional functionalities here, additional functionalities of a Stealth Watch and ICE licenses you get as a part of that Premier license. So actually, you don't have any choice. Let me show you that. You do not have actually any choice, right? So when you order the switches, you have to specify the license that you want to purchase along with that particular switch. That license could be a DNA Essential license, or that license could be a DNA Advantage license, or it could be a DNA Premier license. And this is a subscription-based license. You will not get like a lifetime, subscription for the same. You can go for DNA Essential license in terms of 3, 5, or 7. I think they offer only 3 and 5. DNA Advantage 357, DNA Premier 357 subscription, and the perpetual license is going to be the base license that cannot be purchased as a standalone license, cannot be purchased as a standalone license. This Network Essential is compatible with DNA Essential. So if you want to go for DNA Essential, at least you have the Network Essential license as the base license. And if you want to use the DNA Advantage, you have to have this Network Advantage license as the base license or the perpetual license onto your device, right? So licensing is not licensing is more like a part of your switch purchase itself. Like, you cannot you can upgrade, or you can go for the other licensing later on. But let's say you are not going to take the benefit of the DNA Center at the moment, you can just go with the base license, like DNA Essential license. See, let me show you. So I am at Cisco Commerce Workspace. This is from where we can order the switches, as you know. So I'm going to go catalog. I'm going to go to the switches. Let us purchase the Catalyst 9300 series switch. So I'm going to purchase the switches that I want to use in the access layer. Let us purchase a Catalyst 9300 series switch. So if I go to this Catalyst 9300 series switch platform, these are the models that we have. And you see Network Essential, Network Advantage. So if I want to purchase, like, for example, this SKU, so let's say I want to purchase this particular switch, this particular device. If I want to purchase it, so I'm going to, click on this Add to Cart button. So this comes with Network Essential license. This comes with Network Advantage license. This comes with like Network Advantage, Network Advantage. So you get the licensing from here. I can click on like Configure, and right here, while doing that configure, we can actually choose, see, the DNA license. So this is DNA Advantage license, DNA Advantage DNAC on-prem subscription. right? So this is more like a part of your purchase itself. For 60 month, it is going to be like 595, this much amount of Indian rupees, right? So more like you can say these are the options that you can choose from. These are the options that you can choose from. So the point is that if you go to the software, you will see that, okay, what software is installed. You can go for the DNS Center on-prem subscription, and you can see that you can choose if you want. This is the default that comes. Like you can choose, like you can go for this, or you can go for this, or you can go for this 3 years, 5 years, or 7 years. So based on that, you have to choose at the time of purchase itself. So they have more like made it mandatory that you have to purchase the license for the DNS Center right at the time of purchase, right? So for example, a DNS Center Advantage license for 3-year subscription is going to be like 357,000. That is going to be approximately 3,57,000 rupees, 8,05,95,000. So you can, go on and on and on, and you can check all the rest of the switches as well, but it is going to be part of the switch purchase itself. The licensing is going to be part of the switch purchase itself. So you can say that it is more like a mandatory thing that you have to do while doing the purchase. And of course, like, when you purchase switches in bulk, you get the discount. When you purchase the switches from the partner, you get the discount. So it's not going to be that much. But if I purchase it like directly from here, of course, it is going to cost me that much, and it is also going to add some taxes and everything. So you have to choose based on the same. Yeah. So it goes well beyond 10 lakh. Right? So overall, they have made it mandatory that you have to go for the license. If you don't want the license, go with the basic license so that you don't need to spend a lot of money for the same. And this is applicable for all the switch platforms that are, for example, currently offered by Cisco. This is the license metric, if you say. This is the DNS subscription matrix for the switching. Right? Okay. So yes, you need additional licenses. Those additional licenses are going to come with some additional cost, and it is mandatory for you to actually define what license you want at the time of purchase itself. Even though you are not even going to use the DNS Center in your environment, still you have to do it. Right. Now, the ports. I was talking about the ports. So we have, for example, physical ports. We have ports that we can see where we can connect the devices, such as other routers, such as other switches, such as our end users, such as servers and all. So these are physical ports that we see. But apart from these physical ports that we have on these Catalyst switches, we also have some other ports available onto these switches. Right? So the ports that we have onto this switch, in this Catalyst switch, the ports that we have, this port can operate either as a layer 2 port, or it can operate as a layer 3 port. The port on a Cisco Catalyst switch, a switch port on a Cisco Catalyst switch, can either be configured to operate as a layer 2 port, or it can be configured to operate as a layer 3 port. You cannot do it like you cannot do this in a layer 2 switches. This facility is only available on the layer 3 or the multi-layer switches. So we have the layer 3 switches and the multi-layer switches in our campus area network. The physical switches onto that particular port, the physical ports onto that particular switch can be either a layer 2 port or can be a layer 3 port. So switch port on a layer 3, a switch port on a layer 3 Catalyst, the switch can be configured to operate as either a layer 2 port or a layer 3 port. If this particular port is configured to operate as a layer 2 port, this port must be assigned with a VLAN membership. Otherwise, that port will not be considered as operational. And if the port is configured to operate in as a layer 3 port, then we have to configure the IP address onto that port. Otherwise, the full functionalities of that port are not going to be present. What do I mean by that? That until we configure the IP address onto that port, you will not be able to use that port for traffic forwarding, because the port is operating as the layer 3 port, and we have not configured any IP onto that port, so we are not able to use the full functionality of the particular switch port. Right? So a switch port on the layer 3 Catalyst switch can be configured to operate either as a layer 2 port or as a layer 3 port. Layer 2 ports work based on the VLAN membership, and the layer 3 port must be configured with some IP address so that the port can be fully operational. We can go back and forth between the layer 2 port to layer 3 port, layer 3 port to the layer 2 port by the command no switch port and switch port. So if you go to the port, if you go to the layer 2 port and you want to change it to the layer 3 port, you can actually use the command no switch port, and the port is going to be changed from the layer 2 port to the layer 3 port. This configuration has to be done under the interface mode. And if you want to change the layer 3 port into the layer 2 port, you have to use the command switch port under the interface mode, and the port is going to be changed from the layer 3 to layer 2. These commands, switch port, no switch port, which are responsible to change the port from layer 2 to layer 3 and vice versa, these commands are not applicable on the layer 2 switches. Ports on the layer 2 switches will always be a layer 2 port and must be configured with some VLAN membership so that they can be functional. These commands are only applicable on the layer 3 or the multi-layer switch devices. Remember that if you go under a particular port and we use these commands switch port, no switch port, when the port is converted from layer 2 to layer 3 and vice versa, the configurations on that particular port is erased. So let's say, for example, this port interface FA 0x1, this was part of VLAN 10, and you change that port into a layer 3 port, so this VLAN membership is going to be removed. So you have to be very careful when you are changing the port from layer 2 to layer 3 and vice versa. You have to be very careful while changing the port from layer 2 to layer 3 and vice versa, because the ports that the rules that you change, like layer 2 to layer 3, layer 3 to layer 2, when you do that change, remember that the configurations onto the ports are going to be wiped. The configurations on the port is going to be erased. So when we change the layer 2 port into the layer 3 port, all the layer 2 configurations are wiped. When we change the layer 3 port into the layer 2 port by using the command switch port, all the layer 3 configurations get wiped. So you have to be very careful while changing the port from layer 2 to layer 3. If a port is a layer 2 port or a layer 3 port, how can we check it? So the command is show interfaces, whatever the interface number is, and the switch port command. So if you see the switch port is enabled, then it is a layer 2 port. If you see the switch port is disabled, then it is a layer 3 port. Let's talk about it. So I have a basic, I have one switch here. This is a switch that I am using on my EVNG software. This is a switch that we are going to be using for our this switch port concept. So this switch that we have here, this is a iOS V switch, iOS virtual iOS V switch. I can check that by the command show version. You can use the command show version, and here you can see that, okay, this particular switch is a layer 2 switch. This is a layer 2 switch running on the advanced enterprise license, version 15.2, 2017 release. And yes, that's pretty much it. So this is a basic layer 2 switch. Right now, If I see show IP interface brief, how many interfaces are there? So we have, like, for example, these much interfaces. If I go like show interfaces gigabit Ethernet 0 by 0, and I say switch port. If I use the command show interfaces gigabit 0 by 0 switch port, and if I hit enter, I don't need to worry about all these things. All we need to know, all we need to see is this thing. So if you execute this command and you see that the switch port is enabled, that means this port currently is operating as a layer 2 port. And if it is a layer 2 port, it has to be configured with some VLAN membership, right? And you should know that the default VLAN membership on these Catalyst switches is 1. By default, all the ports on these Catalyst switches, they belong to VLAN 1. What is VLAN? What is all that? I hope you know at least a little bit, but we'll talk in more detail about it later on. So by default, all the switch ports belong to, for example, VLAN 1, and I can confirm it. Once I use this command, first of all, I see that the switch port is enabled, which means that it is a layer 2 port, and access VLAN is 1. That means this port belongs to VLAN number 1. If I want to convert it into the same goes for the rest of the ports. You can check the rest of the ports as well. And if I want to change this port, all I have to use the command is no switch port. Once I use the command no switch port, the port gets changed from the layer 2 port to the layer 3 port. And so the command that I used was interface gigabit 0 by 0 and the no switch port. And if I, for example, check now, I should see so interface is gigabit 0 by 0 switch port. All I see is the switch port is disabled. If you see this, it means that the switch port is not operating as a layer 2 port. It is operating as the layer 3 port. So currently one port is acting as the layer 3 port and rest of the ports are acting as the layer 2 port. So yes, we can put some ports as the layer 2 port and some port as the layer 3 ports. It is completely possible. Right? So if I still go for, like, for example, gigabit 0 by 1, I can still see that switch port is enabled. I can still see that that port is operating as the layer 2 port, but this port is operating as the layer 3 port. And we must configure it with some IP address now. IP address 192.168.10.1. I must configure it with some IP address so that it becomes more like fully functional. Now we have to connect a device out of that port. And once we connect the device out of that port, I'm going to configure the IP address onto that device as well. That belongs to the same network. And we will be able to ping, trace, and do all those things. Do show run interface gigabit 0 by 0. Let us configure some other commands. Interface gigabit 0 by 0. IP OSPF1 area 0. IP access group 101 in. I am configuring a few more commands onto that particular gigabit 0 by 0. These commands are related to IP. And you can see that I am able to run all those commands, all those IP commands, because actually this port is actually a layer 3 port. What I'm trying to show you that if I change this port back to the layer 2 port, you will notice do show run interface gig 0 by 0. You will notice that the all configurations are gone. And if I say no switch port again, if I do the no switch port again, if I convert back it to the layer 3 port, you will not see those commands again. Same if it was a layer 2 port and we did some configuration and we changed it to the layer 3 port, the configurations are not going to be there. So you have to be careful while converting the ports from layer 2 to layer 3, layer 3 to layer 2. You have to be careful. And by careful, I mean you should take a backup of your configurations before you do that change. Now, what do you think? A command is giving me the capability to configure the IP addresses onto that particular switch port. So if I use the no switch port command, it is a layer 3 port. If I use the switch port command, it is a layer 2 port. If it is a layer 3 port, configure the IP. If it is a layer 2 port, configure the VLAN membership and the rest of the commands related to VLAN. A command that is letting us toggle in between the layer 2 and layer 3 switch ports. Does this command actually change the port from layer 2 to layer 3 and vice versa? Is it going to change the properties? Is it going to change the hardware properties of the particular switch port so that it starts operating as a layer 3 port? How can I not do that on the router? How can I not do that on the router? How can on a router, I can just use that router port actually as a layer 3 port only? If that facility is there, why don't they have added this on the routers as well? So first of all, what is going on in the background? What is going on in the background? Once we use that no switch port command onto this particular switch, port number gigabit 0 by 0, to convert that port into the layer 3 port. Why? Because I wanted this user to be able to manage this catalyst switch using telnet SSH, maybe take the backup of the operating system and so we decided to convert that port into the layer 3 port so that I can configure the IP and I can configure the IP. What is going on in the background? Is this port actually converted into the layer 3? Not really, actually. So what happens when we convert this port in a layer 3 port? Switch. What happens? Switch reserves a range of VLAN. Switch reserves a range of VLAN so that that particular range can be used when we do this layer 2 to layer 3 conversion. That range you already know. That range is going to be an extended range. What switch is going to do in the background, once we use that no switch port command, what the switch is going to do in background, switch is going to create an extended VLAN. Switch is going to create an extended VLAN in the background. It is going to map that VLAN with this particular port in the background. It is going to create a layer 3 interface for that particular VLAN in the background. And all the configuration commands that we have executed, all those IP related commands are going to run on this particular logical interface that the switch has automatically created in background. So it is not really changing the port from layer 2 to layer 3. It is just mimicking. It is just, mimicking that we have changed the port. The port is mimicking the role of the layer 3 port. However, that has not done in reality. In the background, once we do that no switch port command, the switch is going to actually create an extended range VLAN. It is going to make the port part of that VLAN. It is going to create an SVI, switch virtual interface, for that particular VLAN. And all the configuration commands that we have configured are going to be executed on that logical interface that the switch has created in background. But for the user, it would look like that all the commands are running directly on the interface. And it is also going to disable all the layer 2 protocols onto that interface. STP, VTP, DTP, everything it is going to disable onto that particular port. This is what happens in background. What happens when we use the no switch port command? In the background, switch reserves a VLAN from the extended range. Extended range VLAN is from 1006 to 4094, which means switch can create any VLAN from this particular range. However, it goes in ascending or descending order based on how we have configured it. So either it will start from 1006 or it will start from 4094. Once it has created an extended range VLAN, it is going to bind that physical port with that VLAN logically. Logically means it will not show you that. It will not show you that. If you use the command do show VLAN brief, it will not show you that it has done that. It will not show you that gigabit 0 by 0 is binded with an extended range VLAN. It will not show you that. It has done it logically. In the background, it has done it. It will not show you anywhere. But that is what happens in the background. And it is going to disable all the layer 2 protocols such as VTP, DTP, STP onto that physical interface. In the background, it is going to create an SVIE for that particular extended VLAN that got created. And all the commands that we run are on that physical interface will run for that particular SVIE. This is what happens in the background once we use that no switch port command. And I can show you that. You want to see show VLAN internal users. It will not show me the SVIE or so. It will not show me the SVIE or so, but we can use this command show VLAN internal users. Once we use this command, we can see what has happened, that the gigabit 0 by 0, which we converted into the layer 3 port, for that particular interface, it has created a VLAN called 1006. It has mapped that port with the VLAN 1006. And it has disabled all the protocols onto that particular interface. And it has configured an SVIE. You can assume an SVIE logically for that particular interface. And all the traffic that that you receive onto that port is logically going to be delivered to VLAN 1006 SVIE, and it is going to be handled based on the same. Right? So it's like that. You send the traffic arrived on the port gigabit 0 by 0. Switch refers to the configuration that this gigabit 0 by 0 is actually a layer 3 port. Why? Because the no switch port command is running. It is going to check this show VLAN internal users. It is going to check that that particular port has been mapped with what VLAN? VLAN 1006. For VLAN 1006, what exactly is the configuration done for the VLAN 1006? What are the IP related configuration that are done for interface VLAN 1006? What is that? IP address is 192.168.10.2 OSPF and all the rest of the commands. It is going to decide based on the same how the traffic is going to be forwarded between these two. See? So I converted all the interfaces into layer 3 interfaces. See, show VLAN internal users. See, show VLAN internal users. Look at that. We can change VLAN internal allocation policy and we can change it in descending order. What do we mean by that? We mean that now if I try to change the ports, such as these ones, interface range gigabit 1 by 0 to 3, no switch port. So if you change that internal allocation policy, command is VLAN internal allocation policy, it will be either ascending or descending. So if you have changed it to the descending order, then what it is going to do, show VLAN internal users. You can actually see that it has started from 4094, 3, 2, and 1. Right? Now, I cannot create VLAN 1006 now. I cannot do that. I cannot create it. If a VLAN is being used by the switch for this internal purposes like this, we cannot create that VLAN. Fail to create the VLAN. VLAN not available in the port manager. Fail to commit the extended VLAN changes. PM port manager extended VLAN in use. VLAN 1006 is currently used by the gigabit 0 by 0. So VLAN creation failed. And if we have configured a particular VLAN, such as 1006, 1007, we have configured, it will not be used for internal uses. So it will create 1008 and map that port when we convert it into the layer 3. Right? There are limitations of the VLANs as well. Like we should not create a few VLANs in a campus network because they are reserved for a few purposes. They are used in a few purposes. So it's always advised that you check out the documents, what VLANs we should not use in our campus area network. There are quite a few ranges that are reserved that you should not use in our campus area network. 1006, is I think like one of them. But the point is, if the VLAN is being used by the switch for internal purposes, you will notice that the VLAN will not be available in the port manager, and you will not be able to create that particular VLAN. That is also the scene, but also some VLANs are also reserved. That is also okay. You cannot use it. Like you cannot use this VLAN 1006. Like you should not use it in anywhere. But that is also seen. But there is also one thing that some VLANs are also reserved. Like some VLANs are also used for some other type of tasks. So you should be careful like what VLAN we create in our campus network. I will try to find that document where they have mentioned it. But there are some VLANs that you have to be careful when you are assigning into the campus area network. But yeah, in this example, if VLAN 1006 is being used for this internal purposes, see, you can use it, but you should not, but you can use it. For example, if there is a user here in VLAN 1006, if you have a user here in VLAN 1006, it doesn't matter because you are not able to see that VLAN 1006 here, and more importantly, it is a layer 3 port. So if it is a layer 3 port, it doesn't matter how the traffic goes outside of it. So you can use it, but you should avoid using it if you have used these kind of things in your network. But you cannot remember like, you cannot remember like what VLAN is being used for the internal purpose, what is not being used. So it will be like hard to maintain the documentation regarding the same. So typically what we do, we change the internal allocation policy to descending so that it starts from the back like 4094, and we are free to use the VLANs from 1006, 7, 8, 9, and then so on. But there is no, like, when it comes to like the documentation, you will notice that they have not mentioned this anywhere that if a VLAN is being used for the internal purposes, we should not use it in a campus, or we cannot use it in a campus. We should not. You can try to avoid it, but there is no hard and fast rule regarding the same. Right? There is no rule regarding the same. Because think about it, it is layer 3. It is all layer 2. So if the traffic even arrives on this particular switch, it has to be routed instead of switched. So it will not be any problem anyway. Right? So this, you can use the command show VLAN internal uses to check what VLANs are being used for the internal purposes. And if you try to create that VLAN, it will just throw us the error that the VLAN does not exist, and vice versa. If you have configured that VLAN, then the switch is not going to use that VLAN for internal purposes. So either you can use it, or that port manager is going to use it for the internal purposes. We can change it. We can change VLAN internal allocation policy descending command. So this command is going to allow the switch to start from 4094 to 1006. ascending command if you use, then it will start from 1006 to 4094. You can always check the command show VLAN internal users to check the output. So the point is, if we change like the port from layer 3 to layer 2, if we change, for example, like port from VLAN 2 to VLAN 3, like L2 to L3, then also in that case, it's not actually really the changing that from one to another. Like it's actually more like mimicking. It's more like making the administrator think that they have changed it, but actually in the background it has used the same VLAN concept, and it has configured an SVI for that particular VLAN to accommodate all to run all those layer 3 commands. Now I could have done it manually as well. I could have done it manually as well. I could have done it manually as well. I could have done it manually if I wanted to. I could have manually created a VLAN such as VLAN 99, right? I could have gone to like interface gigabit 0x0, switch port access VLAN 99. I could have gone to like interface VLAN 99, and I could have configured all those commands right here. What is the difference in those two? Right? I can configure all those things like that as well. But manually going on to the interface, creating the VLAN, going on to the interface, configuring the SVI, it is just too much configuration. It is just, like too much configurations, and you might want to avoid it. So we could have done it manually as well. For example, it was a layer 2 switch. Let's say on a layer 2 switch, it's not even allowed to change the port from layer 2 to layer 3. But I want to configure an IP address onto that switch so we can take the management level of access using telnet SSH. So what can I do? I can go on to that particular switch. I cannot convert that port from layer 2 to layer 3. So I will create a VLAN. I'm going to bind that port with that VLAN, and I'm going to configure an SVI onto that particular switch for that VLAN so that the management can be done of that switch. We could have used that as well. Right? Okay. See, these are some ranges that I was talking about, right? So VLAN 1 is normal, default. We cannot modify, delete it. 2 to 1005, normal. We can create, use, modify, delete these VLANs. 1006 to 4094, extended range. We can create, delete, modify, and these are some results on 3968 to 4047, and there's this one, it is result 80 VLAN plus this one allocated for internal use. We cannot use or delete it. However, this thing only applies for the Nexus series switches. This thing only applies for the Nexus series switches, right? Not on the typical campus area network, but on the Nexus series switches, there are some VLANs that are reserved that you cannot use. These 80 VLANs are approximately reserved for the same. Anyway, so we can actually configure this thing manually as well if we don't want to convert the port from layer 2 to layer 3. Right? So what happens when we change on the layer 3 switches? We can have the port as a layer 2 port. We can have the ports as the layer 3 port. if I change the port from layer 2 to layer 3, this is what happens in the background. It mimics that the port has been changed, but in fact, it is using the same concepts of VLAN and SVIE. It is using the same concepts of VLAN and SVIE for assigning the IP address onto the switch interface. Doubts, let me know. SVI we will talk about just in a moment. We'll talk about the SVI. Our next topic is SVI. Any doubts so far? All right. Now, what is this SVI? What is this layer 3 interface for the VLAN? SVI, switch virtual interface, is a virtual interface that you do not see onto the switch. You do not see these interfaces onto the switch. It is more like a virtual interface that is available onto the switch. So for example, if you don't have a layer 3 switch, then how we are going to configure the IP address on this switch, as these commands that we have covered previously, like IP commands, are available. This is internal use. This is internal use. When we convert the port from layer 2 to layer 3, this is the internal use. Right? So if you do not have a layer 3 switch, we cannot convert the port from layer 2 to layer 3 and cannot configure, obviously, the IP address, because IP address and related commands are commands that we run on the layer 3 switches only. So what we could have done, we can assign the particular port with a VLAN. We can configure an SVIE for that VLAN, and we can give the IP address on that SVIE, and that will be enough. Like, we can use that switch with the help of that particular IP address. So what is this SVIE? SVIE stands for switch virtual interface. It is a virtual layer 3 interface for the VLAN, which is configured with some IP address. SVIE is basically layer 3 interface for a particular VLAN. SVIE, or switch virtual interface, is a layer 3 interface for the VLAN. So I cannot change the port. The port is assigned to the VLAN 99, and I cannot change that port into the layer 3 port. I can configure an SVIE interface VLAN, and I can configure it with the IP address. The example of the internal uses is this: when we change the port from layer 2 to layer 3. This is actually the example of the internal uses. When we change the port from layer 2 to layer 3, switch is going to take a VLAN from that extended range, and it is going to map that range, that particular VLAN with the port internally. So this is an example of the internal uses. Right? So SVI, switch virtual interface, is a layer 3 interface for the VLAN that is configured with some IP address. Because we cannot configure the IP address directly onto the port, because that port will always be, let's say, for example, a layer 2 port. So I can actually configure an SVI for that, a layer 3 interface for that VLAN, and configure the IP address on the same. It allows easier management of the switch, as we can take the telnet SSH access of the switch using that address. In some networks, VLAN 1 can be used for the same purpose. As all the ports are by default in VLAN 1, it will be easy to manage the switches from any device, but it will add the security challenges because everyone knows that by default all the ports are in VLAN 1. So we can choose any other VLAN to be our management VLAN. I can configure like VLAN 999, for example, for our management purpose. We can configure any other VLAN. We can use VLAN 999, configure an SVI for VLAN 999 onto the switch, configure it with the IP address, and that IP address can be used for the management purpose from everywhere. So if I leave the things on default, all the ports belong to the VLAN 1. So we could have just configured the SVI for particular VLAN, SVI for VLAN number 1, configure it with the IP address, and that IP address can be used for the management purpose. But since everyone knows it, that by default every port is in VLAN 1, and you might have configured the IP address in VLAN 1 for the management purpose, no doubt it will be easy, but it will add the security challenges. So we should consider using some other VLAN as the management VLAN in our network. We can create the SVIs on both layer 2 switch and the layer 3 switch, and it can act as the gateway for the users in the VLAN just in case of routing. So the point is, this switch has a few ports where the users are connected, and all the users, let's say for example, these two users belong to VLAN 10, these two users belong to VLAN 20. I want all these users to be able to manage this particular switch. I want all these users to be able to manage that particular switch. The only problem is this port is a layer 2 port, this port is a layer 2 port, this port is a layer 2 port, this port is also a layer 2 port, and we cannot change it into the layer 3 port because let's say it is a layer 2 switch only. So I know that these two users, when they send the traffic will belong to the VLAN 10. And I know that these users belong to VLAN. I know that these users belong to 192.168.10 subnet. And I know that, for example, these users belong to 192.168.20 subnet. So what I can do, I can go on to this switch. I can configure an SVI interface VLAN 10, configure it with the IP address of VLAN 10, and then configure interface VLAN 20, configure it with the IP address of VLAN 20. So now when this switch tries to manage, or this user tries to manage this particular switch, maybe it wants to do telnet, SSH, whatever, it can just use the IP address of the switch that we have configured onto that VLAN 10 for this management purpose. It will send the traffic to 192.168.10.100. Traffic will arrive onto this port. This port belongs to VLAN 10. Traffic will be handed over to the SVI for VLAN 10, and this SVI is going to handle the traffic for that VLAN 10. Same, this user tries to do the telnet SSH onto that switch. This user can refer to the IP address 20.100, and it can use that IP address to do the telnet SSH onto the switch. So when this user sends the traffic to the destination IP 20.100, traffic arrives onto this port. This port is configured in VLAN 20. Switch is going to check the SVI for VLAN 20, and since the SVI is configured with the same IP, it is going to provide the management level of access based on telnet SSH to that particular user. So with the help of SVI, we are not giving IP address to a port. We are giving the IP address to an entire broadcast domain. We are giving the IP address to like entire VLAN. With the help, SVI represents a entire VLAN. SVI does not represent one single port. So let's say we have configured the SVI for VLAN 100, and we have configured the IP address like 100.100. So all the users in the VLAN 100 will be able to use that IP address to, for example, access the switch for telnet, SSH, DHCP, and all rest of the purposes. So SVI, switch virtual interface, is a layer 3 interface for the VLAN. It's more like an interface created for the entire VLAN, not for just a particular port. It is a layer 3 interface created for the entire VLAN, not just a particular port. If I wanted to configure, if I wanted all these users should be able to get the management level of access of the switch, and I want to do it via converting the port into the layer 3 port, then what we need to do? Then I have to configure the port into the layer 3 port, configure the IP. This is layer 3 port IP, layer 3 port IP, layer 3 port IP, layer 3 port IP. I will need 4 subnets in that case. I will need 4 subnets in that case. One subnet, second subnet, third subnet, and the fourth subnet. Because any two interfaces cannot have the same subnet IP. Remember the routing concepts. But it is possible to configure the same with the help of the SVI. Instead of configuring individual IP addresses, or instead of changing it into the layer 3, what we can simply do, I know that all these ports belong to what VLAN? Belong to VLAN 99. So I am going to configure an SVI for VLAN 99, and I'm going to configure with the IP address. And all the users in VLAN 99 can now just use this particular IP address to access the switch via telnet, via SSH, and rest of the services such as DHCP and all, FTP, TFTP and all, you can still get. This is the difference between converting a port as a layer 3 port and configuring an SVI for the particular layer 2 port. We configure the SVI for the entire VLAN. So every port in that VLAN can actually leverage the IP address configured for that particular SVI. Right? Instead of just converting the port into the layer 3, configure it IP address, because that will require too many IPs in that case. Right? So how can I do that? I can do it like this. Here, I know that interface gigabit 0 by 0 belongs to VLAN 99, so I can configure an SVI for that particular VLAN. And now I can just connect, let's say, for example, I can connect a user. I can simply connect a user onto the gigabit 0 by 0. Here, I can connect the user. I can configure the user IP address from the same subnet. So what IP I have given? What IP I have given to that particular VLAN 99 is 192.168.10.1. I can click on that, and I can configure the IP address 192.168.10. Maybe what IP was there? 10.1, right? So 10.2, 255, 255, 255.0, and 192.168.10.1 is the gateway. IP, I am configuring the IP address onto this device, 192.168.10.2, subnet mask, and the default gateway. This port is not a layer 3 port. This port is just a layer 2 port. This port is a layer 2 port. Interface gigabit 0 by 0. See, so VLAN brief. Interface gigabit 0 by 0 is a layer 2 port. It is part of VLAN 99. For the VLAN 99, I have configured an SVI, switch virtual interface. It is down. I have to make it up. The interface VLAN 99, and I have to do a no-shut. We don't need to do no-shut in the real devices. Since this is a virtualized environment, here we might need to do the no-shut so that the SVI comes up. Right? So this is up, up. Now, if I go here, try to ping 192.168.10.1, I'm getting the reply. I am getting the reply from 192.168.10.1. So when I send when I send the traffic to 192.168.10.1, traffic arrives onto this gigabit 0 by 0. Gigabit 0 by 0 belongs to VLAN 99. So the traffic is handed over to the SVI for VLAN 99. And this SVI is responding. You can check it to IP, ARP, and everything. See? Now I can connect another user. I can connect another user on the interface gigabit 0 by 1, for example. I can configure another user in interface gigabit 0 by 2, for example. I can put these interfaces in VLAN 99. They will just be able to access the switch based on the same IP address. I don't need to configure the IPs here individually. This is the advantage of using the SVI than converting the interfaces as the or in the layer 3 interfaces. Now, this SVI, sometimes it is up, sometimes it is down. So for example, if there is no user in that, for example, VLAN, there is no user in that VLAN. There is no user in that VLAN, 99, for example, then this SVI will automatically go down. So for the SVI to remain up, there are conditions. For the SVI to remain up, there are conditions. For the SVI to remain up, there are conditions. What is the condition? Condition is that, let's say we are talking about the SVI for VLAN 99. There at least have to be one active port in that VLAN 99. Then only SVI will be up, otherwise SVI will be down. If you do not have the port, you should have a trunk port, and that VLAN should be allowed onto that trunk port. Then also the SVI will remain up. So once we create the SVI goes in up state automatically. But if the SVI is not going into the up state, make sure that you have at least one user, one port assigned to that particular SVI, assigned to that particular VLAN, and that port is up. Or make sure that you have a trunk port and that particular VLAN is allowed onto that particular trunk port. Yes. That means that if the user, for example, has the user ID and password for this particular switch, the user will be able to access that switch. And if you don't want to allow it, you can configure the ACLs and you can control like under the line VTY. For example, you don't want to allow the particular users to do telnet SSH, these kind of things. You can always add on some additional security for the same based on things such as access list. Or we can also, of course, that we can also integrate it with AAA so that the user credentials are authenticated via AAA. And then the authentication is either allowed or denied. So we can have a level of control from AAA as well. We can have AAA on the local, or we can have AAA on the server as well. So we can control it. But we need an IP. For the switch to be able to be managed, we need an IP. That IP can either be on the physical switch or that IP can be configured to an SVI. Remember, SVIs are different than the loopback interfaces. Loopbacks are also there. Right? Loopbacks are also there. So we have physical interfaces onto the switches. Then we have logical interfaces on the switches. Logical interfaces include SVI and the loopbacks. And do not forget about HSRP, VRRP. There we have the virtual IP. That concept is also there. So we have different types of interfaces onto the switches. Can we have trunk port and SVI in the same VLAN? No problem. Like let's say, for example, we have two switches connected like that. And here we have a user. The user is in VLAN 10. For VLAN 10, we have configured the SVI. And here also, like we have configured this trunk port. And onto this trunk port, that VLAN for VLAN, that VLAN 10 is like, for example, allowed. And so yeah, we can have that scenario as well. Like there is no restriction for the SVI. We can create the SVI for the VLAN and that is it. Where we have to use it or where we want to use it, that is completely on to us. If you do not want to allow the traffic for VLAN 10 to pass, we can control it. But if you don't do anything, by default, all the VLANs are going to be allowed. So there is no such restriction for the SVI. SVI differs from the loopback based on the same. Loopback again represents one single interface, a layer 3 interface configured with the IP address. However, the SVI does not necessarily represent one physical interface. It represents a group of interfaces belonging in a particular VLAN. So it differs from that. SVI differs from the loopback from that point of view. Right? SVI is for the entire VLAN. Loopback is just an interface. It's like a layer 3 interface that we have on the switches, on the router, just like that. And the SVI is for the entire VLAN. So every interface in that particular VLAN will be able to access the services of the switch based on that SVI IP address that we have configured. Right? So this is about the SVI. This is about the switch virtual interfaces or SVI. Now we will talk more about this Cisco Discovery Protocol, CDP, LLDP, and we will talk about lab, how we are going to do the lab. Typically, we do not have SVIs on the router. We do not have VLANs on the router, but we do have VLANs on the router. You will notice that typically we cannot configure the VLAN membership on the router, but when we use the router to perform things such as inter-VLAN routing, we create the sub-interfaces, and routing on a LAN sub-interface is only allowed when it is part of a particular VLAN. So yes, we do have VLANs on the router, but not directly, not like the switches. We do have VLANs on the router, but typically in the scenarios when we perform things such as inter-VLAN routing, and we have configured the sub-interfaces. So in the sub-interfaces, VLANs exist on the router. So we'll talk more about protocols, CDP, LLDP. We will talk about the lab that we are going to use in our practice sessions. Like we will have one lab, and in that lab we will be doing all these things. So we will create a lab in this topology. We are going to create a lab in here, and we are going to use that lab. We will be using that lab for the rest of our classes. Right? And if anything is required on the physical devices, I will show you that on physical devices as well. I do have a rack, so I will be able to show you that on the physical devices as well, just in case if it is required. So you can use like EVNG, or you can use this PNet, lab, which is just better comparatively. So I'm going to use this EVNG software to, create a basic topology in which we are going to do all our lab. So just to give you the idea a little bit about the topology, when we design a Swiss network, typically we have a few layers that we should consider while creating the Swiss network, such as the access layer. We'll talk about this in detail later on. So access layer, then we have this thing called distribution layer, and then we have this thing called core layer. So if you have a very big campus network, you can have like all these three layers: access layer, distribution layer, and the core layer. But if you have, let's say, for example, a small to medium campus area network, you can have like access layer, and the responsibilities of distribution and core layer can be merged together in one single layer called core distribution layer. Right? So we can have either 2-tier model or we can have a 3-tier model. At the moment, I'm going to go with the 3-tier model, where we are going to have a few devices at the access layer, and I'm going to have a few devices at the distribution layer, and then I'm going to have a few devices at the core layer. So these 4 switches that we have, switch 1, switch 2, switch 3, switch 4, they are at the access layer. I'm going to use a few more switches here. I'm going to use 2 switches for the distribution layer. So I'm going to use like 2 switches at the distribution layer. So let me color it like blue. So I'm going to use 4 switches. I'm going to use like 4 switches at the access layer, and I'm going to use 2 switches, the switch number 5 and switch number 6 at the distribution layer. And then I'm going to use, considering that my campus area network is quite big, I'm going to consider a few more switches, like 2 more switches at the core layer, right? So we have like these 2 switches more at the core layer, and then these switches can go, these core layer devices that we have here. These core layer devices can further go towards the routed network, such as we can have a few routers here as well. So let me add 2 routers, and I'm going to represent one router. The router that is going to go towards our public network, such as internet. So I'm going to use this one router, right? This router is going to go towards a public network, such as internet, and we can have one more router that goes towards the other service providers, such as MPLS also. So I'm going to consider like one more router that is going towards the private transport, such as MPLS. Completely your choice if you want to add the routers. I am going to add the router because we are going to use later on HSRP, VRRP and all. So it will be beneficial to see how this works. I'm also going to add a few VPC, like virtual PCs. So 8 number of virtual PCs I'm going to add. I'm going to name it like host. So host 1, 2, 3, 4, 5, 6, 7, 8. These 8 devices I'm going to add. Okay. Here, then here too, then 2 here, and 2 are going to be here, right? So let me just rearrange it a little bit. So we have switch number 4 there. We have like 2 host machines connected, host number 7, 8. Here on the switch number 3, we have few devices connected. On the switch number 2, we have few devices connected. On the switch number 1, we have a few devices connected, right? So this is how the topology is going to be. And quickly, just so that we don't have any, just I'm going to name it as 1, 2, 3, 4, 5, 6, 7, and we are going to interconnect them with the help of like one cable or 2 cable, maybe, completely your choice. It is mostly because of this browser. So you can rejoin once, it will fix automatically. Like you can rejoin once if there is if there is a lag in the audio. You can rejoin once, it will fix actually. Right. So let us connect all these. So this is Ethernet 0 by 0, 0 by 0. This is going to be 0 by 0, 0 by 1. This is again going to be 0 by 0. This is going to be 0 by 1. This is going to be 0 by 0. This is going to be 0 by 1. This is going to be 0 by 0. And this is going to be 0 by 1. Right? And I'm going to connect all of them to switch number 5. You can connect them like with whatever cable you want to connect, completely your choice, right? So it's not like you have to have the exact same number. So at the moment, I'm going to connect it like that. We can have redundant links as well. I will add the redundant links later on. We can have like more than one links, but I will add the redundant links later on. Right at the moment, we just have like one link from the devices to there. I also have to edit it, and add more Ethernet interfaces. So instead of one, save and wipe, and I will restart later on. Right. So I'm going to connect it like that on all the switches. Okay, here also same thing. Edit. I'm going to add 4 more interfaces. Save. I think we ran out of interfaces. Yes. So here also edit to note that interfaces are completely random. So I have not connected like a specific interface to a specific one. It is completely random. Right. So something like that we are going to have in our topology. Right. So and then further on it can go towards the other, for example, public networks such as internet, or a private network such as MPLS to connect it to our branches, and so right. So we can also have the connectivity to the rest of the places based on the same. We are not too concerned about the connectivity to the external network or at the moment. We have to just see the switching part in our campus area network. Right. So rest, like, we don't need to worry about it. So what we are going to do here, let's power on the devices. So I'm going to power on. First of all, I'm going to save this. Right. So same here, lock. And then I'm going to power on all devices. Okay. So first thing that we have to see today. First thing this is the topology that we'll be working on from now on. This is going to be the topology. And in this topology, we have like a few access layer devices going towards some end user. We have a few, distribution layer devices. Then we have a few core layer devices. And then we have some internet edge routers, and let's say the service provider edge router. So we can also connect to these service provider network based on the same, like networks such as MPLS or so, or we can connect to the public network such as internet. Right. So we will be working on this topology throughout our content. And in this topology, we are going to configure like VLANs, VTP, DTP, STP, everything we are going to configure in this one. Right. So for today, first thing that we have to cover today, the first thing that we have to cover is this device discovery. How can we discover the devices? How can we discover the devices with the help of CDP and LLDP, Cisco Discovery Protocol and Link Layer Discovery Protocol. Right. So we will talk about how can we for example, discover the devices. So I have powered on all the devices that we have here. I have powered on all the devices, and we are going to actually configure. We are going to see the use cases of the CDP and LLDP, Link Layer Discovery Protocol, in this current topology. We will see how can we discover the devices based on CDP and LLDP, and then we will move further to the design part, which we have already done just now. So we will explain. We'll try to see how this design actually happens in this infrastructure. Right. So CDP, Cisco Discovery Protocol, or Link Layer Discovery Protocol, CDP, LLDP, these are two protocols that we can use for device discovery purpose, or more like network discovery purpose. So we can have, for example, like a few set of devices, few set of like Cisco devices, routers, switches, other devices as well in our campus area network. And we might want to discover those devices. Like I am having the access of like one of the device. Let's say, for example, I have the access of switch number 1, and I want to see what are the directly connected devices, what are the devices connected with switch number 1. I want to check that. I want to get the information so that I can build a topology based on the same, for example. So to do that, what we can do, we can use this protocol called Cisco Discovery Protocol, or we can use this protocol called LLDP. So CDP and LLDP, these are two protocols that we can use for device discovery purpose. Both are layer 2 protocols. Both protocols that we are talking about, both are the layer 2 protocols. They both work at the data link layer, right? And they are, for example, like CDP is going to discover the basic information about routers and switches. Here it should be like about routers and switches without needing to know the password for those devices, right? So with the help of the Cisco Discovery Protocol, we can actually discover the information about the routers and switches without needing to know about the passwords of the neighboring devices. To discover that information, devices are going to send the CDP messages, routers and switches are going to send the CDP messages out of all the interfaces where the CDP is enabled. And this message essentially announces the information about the device that sent the CDP message. So for example, in our topology, when the devices boot up, switch 1 is going to send a CDP message to all the neighboring devices that it has, and it will receive the CDP messages from all the devices that it has. And based on that, we can confirm, we can check on that switch number 1, what are the directly connected devices connect on that particular switch number 1. So I can, for example, open this here. This is switch number 1. I can go to the switch number 1 and I can see the information. CDP is by default running. You can check the information if the CDP is running or not. Show CDP on interface. You can check this information about the CDP on a particular interface, such as 0x2. You can check if the CDP is running or not. So it says that sending the CDP messages in every 60 seconds and the whole time is 180 seconds, which means that the CDP is running on that particular interface. So show CDP interface, you can use this command to check this information about the CDP on one particular interface. And if you do not mention the interface, it will show you the information on all the interfaces, right? It will show you that, okay, CDP is enabled on total 4 interfaces and 4 interfaces are up. So you can use the command show CDP interface, or you can use the command show CDP interface and then the interface number to get the information about the Cisco Discovery Protocol if it is running onto that particular device. Now, if I use the command show CDP neighbors, I will be able to see the information about the CDP neighbors here. So I am at switch number 1. Remember that I have not configured anything on here. No, like, host name, nothing. We have not configured anything here. That is why the device name is set to default switch. So this information says that this switch is connected to 2 neighboring switches. One device is named as switch. The other device is also named as switch. Your local interface is 0x2 and 0x3. That means your interface 0x2 and 0x3, they are connected with the neighboring devices. And on the neighboring devices, the interface is 0x0, and the neighboring devices, the interface is 0x0. Right? So this is your interface, this is neighboring device interface. This is your interface, this is neighboring device interface. What is the platform on that particular neighboring device? What is the platform of that particular neighboring device? You can see that here as well. So if it was, for example, a real environment like we had, like let's say, for example, we are using the command on this real devices, it will show you the platform information of that particular device, such as 2950, 2960, 37, 38, whatever switch platform it was, it will show you that there. Then Hold time information 180 seconds. So the timer starts from 180 and it goes all the way to, it starts from 180 and it goes all the way to 120. So it starts with 180 and it goes all the way to 120. As soon as it reaches to 120, it receives the CDP message from the neighbor router. Why? Neighbor switch. Why? Because CDP messages are sent in every 60 seconds. So from for example, from 180 to 120, 60 seconds will pass. So once it reaches to like 120 mark, it will receive that CDP message. It will receive that CDP message and the timer will reset actually. It will receive the CDP message and the timer is going to be reset. So fine. So in every 60 seconds, CDP information is actually exchanged between the devices. It also tells the capability. It also gives the capability information. Capability means like what capabilities are enabled onto that particular device, like routing capability, switching capability, IGMP capabilities are there. So it shows like what capabilities are currently enabled onto that device. This is not representing, this is not showing exactly correct, because by default routing capabilities are not enabled on the switches, right? So ideally it should only show you like S and maximum to maximum I stands for IGMP. So capabilities, it shows like what capabilities are enabled, on the neighboring device. So routing, switching, IGMP support is there. So all these three capabilities are enabled on the neighboring device. That information I can check from here. Right. So this is in brief. Now let me do one thing. Let me try to change the name. For example, let me go on the switch number 5 and switch number 6, and I'm going to change the host name on here. So I'm going to say like configure terminal, host name, switch number DS, switch number 5. Right. So distribution layer, switch number 5. Yeah, just give me a second. DSW5. This is the name that I'm going to give for this particular switch. And I'm going to give the name to this particular switch as host name DSW6. Right. So I have changed the name. I have changed the name on this switch number 5. I have changed the name on switch number 6. And if I go to switch number 1 again, and if I check the information, it says that there are 3 switches now. It's not like 3 switches actually. This information will age out, or this information will age out once 120 seconds, like once that whole timer expires. So now the switch is receiving the information from switch number 5 and switch number 6. It is receiving the CDP messages from switch number 5 and 6. So that information it has maintained here, but this information it is going to age out after that whole timer completely expires. That means this information is still there for 180 seconds. This information will still be there for 180 seconds. And once that timer expires, this information will go away and you will only have the information about the devices. So the point is that once the information is there in the CDP table, the information is going to remain there for 180 seconds, even if I am not receiving any CDP message from the neighboring device. And once 180 seconds have passed, then only the information will age out, and you will have the information about only those devices from where you are receiving the CDP messages. Or you can just use clear CDP table command, for example. You can use the clear CDP table command a few times, show CDP neighbor, and CDP neighbor, it should clear. See, the whole timer it cleared actually. So the information is gone. So once you use the command, once you use this command, clear CDP table, it is going to set the whole timer as 0. And as a result, the information is going to age out. And now we will wait for the CDP message from the neighbor devices. And once I receive the CDP message from the neighbor devices, I will have the information, what switches are connected, what devices are connected to me on here. And also remember that I have not configured any IP address also. There is no IP address on the switches. There is no IP address on the router. It is pure layer 2. Like these all messages are completely layer 2 messages. So we do not need any other credentials or anything, username, password or anything. We don't need actually. right? Nothing I don't need. So that information is here, right? So this is in brief. This is in brief. If you want to check the information in detail, to CDP neighbor, you can also check the neighbor on any specific interface, such as, for example, Ethernet 0x2. You can check the information on a specific interface that show me the CDP neighbor onto that particular interface, show CDP neighbors. And here we have like a lot of commands here. So you can check the information like show CDP neighbor detail. If you want to check the information in detail, enter. So it will show you that what are the CDP neighbors. It will give you the information in very detail about those CDP neighbors. So it says that there is a device called DSW5, right? It is more like what platform it is. So like 2950, 2960, whatever it is. Then capabilities, what capabilities are enabled there? What is your interface? What is outgoing interface? That means your interface Ethernet 0x2 is connecting towards the outgoing, the other side interface 0x0. Hold time is 180 seconds. Hold time is 180 seconds, actually. That is decreasing. And if this timer goes to 0, it will clear actually. So it says the hold time information. Hold time is 180 seconds. What version is running on that particular neighboring device? CDP advertisement version 2. VTP domain name, we have not configured. Native LAN, duplex, these are some general settings that are carried in the CDP message itself. Right, so CDP is going to carry all that information. So just in case if your VTP domain name, for example, mismatches, in that case, you will get some CDP error messages. Just in case if your native LAN mismatch happens, then you will get some error messages. Just in case if your duplex mismatch happens, then you will get duplex mismatch messages as well. Right, so since CDP carries the information about the VTP domain name, native LAN, and the duplex information, so if the mismatch happens, you will notice the logs from CDP itself saying that, okay, domain name mismatch has happened, native LAN mismatch has happened, and all those things. It will show you. So you can check the information in detail. You can check the information in detail with the help of this show CDP neighbor detail command as well. Other commands are available. You can see the other commands. These are other commands that you can also use to check the information about CDP on any particular, for example, interface, on any particular interface in detail, and so on. You can check all that information based on the same. Now, if you want to disable the CDP, very simple. You can just say no CDP run. It will disable the CDP onto the switch. So you can use the command no CDP run to disable the CDP onto this particular Catalyst switch platform. So now if you say show CDP neighbor, it will just say CDP is not enabled. So you have disabled the CDP like that. If you want to enable the CDP, you can use the command CDP run. You can also on per interface basis, you can say CDP enable, or you can say no CDP enable. You can also enable disable CDP on per interface basis. So sometimes like you might want to disable the CDP in your environment, such as, for example, on these like these core routers, for example, these routers that are going towards the service provider network or the private service provider such as M+ network. So I don't want to give the information about my router to the provider. I don't want to give the information to the router about the router to my provider. So here you can disable the CDP either globally or on the particular interface, completely your choice, completely your requirement. You can disable the Cisco discovery protocol onto the devices based on your requirement, or you can let it run as it runs by default. The only challenge in CDP protocol, the only challenge that you will notice in the Cisco discovery protocol is that it is Cisco proprietary. That means other vendors, they don't have any option to implement this CDP protocol in their network. Now, native LAN and everything we will cover in trunking. So CDP, Cisco discovery protocol, CDP protocol runs on the Cisco platforms. But if you do not have, for example, a Cisco platform, you can use an open standard protocol called LLDP, or link layer discovery protocol. So if the commands remain same, you just need to replace the keyword CDP with LLDP. So show LLDP neighbor, show LLDP neighbor detail, show LLDP neighbor detail, show LLDP for example, neighbors on Ethernet, 0x0, 0x2, whatever it is, detail, like, the commands remain the same, the syntax remains the same. You just need to change the keyword CDP to LLDP. CDP is not running by default. You can, LLDP is not running by default. You can use the command LLDP run, so that LLDP starts running on this switch platform. And you can use the same command LLDP run here. And you can use the same command LLDP run here. So you can enable disable LLDP by the command LLDP run. You can enable disable CDP by the command CDP run in the global configuration mode. You can also go to the interface, such as interface Ethernet 0x0 LLDP transmit. So you can say no LLDP transmit. That means you don't want to transmit any LLDP messages, or you want to transmit the LLDP messages and LLDP receive, or no LLDP receive to control on per interface basis. Do you want to transmit and receive the LLDP messages on the interface or not? So just like CDP, we can also control on per interface basis that do we want to enable the LLDP on per interface basis or not. The difference comes like in between CDP and LLDP, that when we use the command CDP enable, no CDP enabled on the interface, it will either enable or disable CDP onto that particular interface. We cannot say that, okay, I will only send the CDP messages, but I will not receive any CDP messages. That facility is not there. That is available in this Cisco Discovery Protocol here. That is available in this LLDP protocol here. So link layer discovery protocol has the capability to send the LLDP messages on a particular interface, or not send the LLDP messages on the particular interface while still receiving the LLDP messages onto that particular interface. So I will get the neighbor information, but neighbor will not get my information. Something like that we can do if it is required. So on per interface basis, we can control in LLDP, do you want to transmit? Do you want to receive the LLDP messages or not? That cannot be done for CDP. Now, if I use the command again, show LLDP neighbor, LLDP messages are sent in every 30 seconds, and the whole time for the LLDP message is 120 seconds. So if I use the command show LLDP neighbor, we can see that the almost similar type of thing we see here in the show LLDP neighbor. I can see my neighbor switches, I can see the interfaces, and whole time is 120. This R stands for router, so it's actually not a router. It should show you B here. B stands for bridge. So remember that we are working in a simulated environment, so not everything is going to be correct. So this should be B. B stands for bridge. So since it is switch, actually, I think we have it is a switch actually. So it should show you B here, not R. So B stands for bridge, or it should show you switch here, S. In the CDP, it shows switch. In the LLDP, it shows B, bridge. Right? And the outgoing port, like your interface Ethernet 0x2 is connected to Ethernet 0x0 of switch number 5. If I use the command show CDP, show LLDP neighbor detail, if I use the command, so I will see the information in very detail. And LLDP, like for example, on your local interface Ethernet 0x3, there is a device with chassis ID, then the port, then port description, system name. Yeah, like out of your interface Ethernet 0x3, there is a device connected distribution layer switch 6, DSW6, and the port is basically like Ethernet 0x0, and that has the chassis ID, this one. The description, the messages, capabilities, enabled capabilities, it should be B actually, not R, it should be B. So management address, we have not configured any IP address onto that switch. Auto negotiation, physical media capabilities, VLAN ID. So different information is advertised in the LLDP messages. Both the protocols, CDP and LLDP, both the protocols are used for the device discovery purpose. LLDP is defined in IEEE standard 82.1 AB. LLDP provides a standardized protocol that provides some general information, same as the CDP. It has similar configuration and practically identical show commands as compared to the Cisco Discovery Protocol. So just replace the keyword CDP with the LLDP, and you will know all the commands about the LLDP as well. right? So based on if you are running two Cisco devices or you're running Cisco device and a non-Cisco device, you can use either CDP or LLDP to discover the device information, right? So let's say I did not know the topology about the network, so I can use the CDP to discover at least what are my directly connected devices. And if I have configured an IP address here, that IP address will also be announced on system number one. So once I get the IP address of that neighbor, I can telnet or SSH to that particular neighboring device, and from there I can use the source CDP neighbor and get the general information about the topology. I will get the IP address of the neighboring devices, management IP of these neighboring devices. I can jump on these management, like I can jump with the help of this management IP on these neighboring devices, and there I will run the source CDP neighbor, CDP neighbor, CDP neighbor on all these devices, and I will be able to build a topological construct, basically a topology information just based on the CDP messages. Right. So Cisco Discovery Protocol (CDP) can help us in identifying what devices are connected to a particular device as in a directly connected fashion, if I say. Right. So CDP and LLDP, Cisco Discovery Protocol, and LLDP protocol, they both are used for device discovery purpose. Right. Okay. So what we are going to do here, now I'm quickly going to change, for example, the name of all these devices. On all these devices, I'm just quickly going to change the name of all these devices. And I'm going to use some general commands. Right. So let me just quickly access all these devices. Switch number 1 is already there. Switch 2, switch 3, switch 4, switch 7, switch 8, router 1, and router 2. Now some general commands I'm going to use here. General commands I'm going to use on all the devices. Some general commands I'm going to use on all of these devices. So just give me a second. So right. So enable configure terminal. Right. So first of all, hostname as hostname I'm going to change later on. So no IP domain lookup, so that if I accidentally put incorrect command or something, it doesn't start translating to the domain server. Line console 0, logging synchronous, and exec timeout 00. Terminal history size I'm going to configure 200 and save it. So some general commands I have configured, like on all the devices, I have configured some general commands, and then just I'm going to change the quickly like host name on all the devices. So this is going to be like R1, this is going to be like R2, this is going to be like switch 1. So access layer switch 1, right? This is going to be access layer switch 2. This is going to be access layer switch 3. This is going to be access layer switch 4. And this is going to be distribution layer switch number 5. And this is going to be distribution layer switch number 6. And this is going to be core layer. So I'm going to name it as core layer switch 7. And I'm going to name it as core layer switch 8. And I'm going to save all the configuration. Right. So we can build the network based on those CDP LLDP messages. We can use CDP LLDP to build the network, build the topology, or get at least the information about the directly connected devices with the help of those, those things. So we can discover the devices using CDP and LLDP. Now remember that there is a lot of information that is carried in the CDP and LLDP. We can control what information to actually advertise in the CDP LLDP. We can also do that as well. History size basically means like when I do this show history, right? So how many commands will be shown here? So remember that this is a simulated environment in this what is this software? It actually how many number of commands can be stored in the history buffer. So that is history size. It doesn't show you history on the routers. Remember that. This software that we have here, EVNG platform, it does not show you history on the routers. That is why I do not use this in the routing classes, because there we need the history and all. So generally for the routing classes, I use GNS. Right. Now I can control, like I was saying, I can control, like we have like time, we can change the timers, CDP timer, how long, the rate at which CDP messages are sent. I can say like CDP hold time 180. I can change the timer as per my requirement. I can go on the interface such as Ethernet 0x2, and I can say like CDP enable or CDP disable. I can do that on the per interface basis. But apart from that, there are other commands as well, such as, for example, changing the timer, hold timer, or we have this CDP timer that says that CDP messages will be advertised in how many time period. Right. Then we can also add the like insert the interface IP address in all the CDP message. We can also add the IP address of a particular interface in all the CDP messages. That command is there. We can log the messages generated by the CDP. So there are other commands as well. Now, this TLV list or TLV stands for type length value, right? So this TLV stands for type length value. So we can specify what type of information can be carried in the CDP messages. So for example, this CDP, in Cisco Discovery Protocol, we do not get much option that to control like what information we want to advertise, what information we don't want to advertise in the CDP messages. So app specific type length value, there is something like app specific type length value TLV information that you might be able to advertise certain app related information in the CDP messages. That is only there. If you go to like interface and there you use the command CDP TLV, you have again the option to enable or configure the application specific type length value. Type length value basically means like what type of information it is, what is the size of that information, and what value. So for example, here, if I use the command show CDP neighbor, here or show CDP neighbor detail, whatever it is. Oh, on here. So CDP neighbor, for example, this output is showing me that there is a device switch number 5 connected onto your interface 0x0. So if I check the information in detail, for example, this. So type is what? VTP management domain. Length is the size of that management domain length, and X bytes. And then value means whatever domain name you have set, like Cisco. So in CDP, all the information is sent in the format of TLV. TLV stands for type length value. For example, type is duplex. CDP is advertising the duplex information. Length, size of that information, and value means full duplex or half duplex, for example. So in CDP, the information is advertised in the format of TLV. TLV stands for type length value. And we do not have much control on like what information can be advertised, what information cannot be advertised. We just have the option to configure some application specific TLVs, could be related to certain applications in your infrastructure, but we don't get much options to configure or to choose from, like what, for example, information is going to be advertised in that particular CDP message. But when it comes to LLDP, we can actually choose from these things. We can choose from these things. Like, do you want to advertise the system description? So I can say that in the LLDP messages, I also want to advertise the system description, or I don't want to advertise the system description, or I want to advertise the system name, or I don't want to advertise the system name, for example. So these are TLVs. TLV stands for type length value, that can be used to advertise a certain information to the neighboring devices or not advertise certain information to the neighboring devices. LLDP gives us much more control over CDP when it comes to like what information we want to advertise to the neighboring devices and whatnot. Right? So it's not like CDP is bad or something like that, but it's just the level of control that we get in the LLDP is much better or much more than that we get in the CDP, Cisco Discovery Protocol. Right? So we can also control what information needs to be advertised, what information need not to be advertised in this command, CDP TLV select or in these commands. Right? So that's pretty much it about the CDP and LLDP. That's almost like pretty much it about the Cisco Discovery Protocol and the LLDP protocol. Just remember that both of these protocols can be used to discover the device information. Right? So CDP, LLDP is now done. Now, we have already talked about these different types of switches that we have in our network. We have like Catalyst 9000 series switches, Catalyst 3000 series switches, 4000, 6000, and the other series switches. Now, when it comes to designing a campus area network, when it comes to like building a campus area network, what options we get actually? That we have to talk about now. So when we want to design, for example, when we want to design the campus network, how we are going to design that? When we want to design the campus local area network, how we are going to design the campus area network? Now, to design the campus area network, actually, if you want to design the campus network, actually, you have to follow either 2-tier or 3-tier hierarchical model. Either you can go for this 2-tier hierarchical model, or you can go for 3-tier hierarchical model. So when it comes to like 3-tier hierarchical model, in that case, there are 3 layers in the hierarchy. One is called access layer, one is called the distribution layer, and one is called the core layer. But when it comes to like 2-tier hierarchical model, it has only 2 levels of hierarchy in the design. One is like access layer, and the second one is core distribution layer. So in a small to medium campus network, 2-tier works best, and in a very large campus area network, you should go for this 3-tier design. So if you have like multiple campuses and you want to connect all those campuses together, we have like multiple buildings. Every building has an access layer device and the distribution layer device. Let's say we have 3 buildings, for example. We have 3 buildings or 5 buildings in our campus area network, and every building has a few like 10-20 devices at the access layer. It has like 2-4 devices at the distribution layer, and we want to connect all those buildings together. So in that case, since we have like quite a big campus area network in this case, we might want to go for this core layer. Otherwise, in typical, we do not need the core layer. Just 2 layers will work fine. Right. So in the 3-tier design, we have 3 levels of hierarchy. In a 2-tier design, we have 2 levels of hierarchy. 3-tier hierarchy has 3 layers in the design. 2-tier hierarchy has 2 layers in the design. In a large campus network, 3-tier works best. In a medium to small campus network, 2-tier is actually going to work best. Now, what is this access layer? What is this access layer and what are the properties of the devices that we are going to connect at this particular layer. So access layer exists where the end users are connected to the network. So in the design, at whichever point the end users are connected, that layer is typically referred to access layer. Like for example, this switch 1, 2, 3, 4, these all the devices are going to be referred to as access layer devices because they provide the user connectivity to the network. Like they connect the users to the network. So these devices are going to be referred to as like access layer devices. Access layer devices connect the users to the network, and the users could be like simple PCs. It could be like there could be like server. There could be an access point that connects the wireless users accordingly. So it could be an API as well. It could be a host. It could be a laptop. It could be a desktop. It could be a server. Anything. Any host that gets connected to the network, it is going to connect itself on the access layer. So access layer is the point. Access layer is the point that connects the end users to the network. So access layer exists where the end users are connected to the network. Access layer switches usually provide layer 2 connectivity between the users. So on the access layer, VLANs exist. On the access layer, VLANs exist. On the access layer, we have to configure VLANs. On the access layer switches, we are going to configure the VLANs, and we are going to put these users in a particular VLAN. So access layer switches, they provide VLAN connectivity. Access layer switches, they provide VLAN connectivity to the users. Like access layer switches are the places, access layer switches are the devices where we define like, okay, this user belongs to this particular VLAN, and based on that VLAN, the user is supposed to access a certain services. The devices that we connect at this layer, they are also called like building access switches. And whatever devices that we connect at this particular layer, it should have following capabilities. So the devices that we connect at the access layer, it should have these following capabilities, like low cost per switch port, high port density, scalable uplinks to the higher layers, high availability and port security, ability to converge the network services such as data, voice, and video, security features such and quality of service features. So whatever device we connect at the access layer, they should have at least all these facilities. First facility is what? This low cost per switch port, high port density. What do we mean by this? We mean that the device that we connect at the access layer, whatever device we connect at the access layer, it should have a lot of ports. Because at the end, from the access layer, end users are going to be connected, and end users can be like 10 users, 20 users, 30 users, 50 users. So it says that these access layer devices should have like a high port density. That means the number of ports on those access layer devices should be higher. Like there should be a lot of ports on the devices that you are going to connect at the access layer. So you should connect a switch at the access layer. You should add a switch at the access layer where we have like a lot of ports, right? And the cost per port should be low. What do we mean by this? Cost, don't think like that OSP of cost. It's money. It's cost means like, money actually. So let's say we have two options. We can connect this switch, or we can purchase this switch and install it at the access layer. Both the switches come with 48 ports. Like both the switches actually have 48 ports, and both the switches we can add on the access layer. The difference is this particular switch that we have, this switch number 1, is going to cost us approximately, let's say, $2,400. And this switch, for example, that we have here, it is going to cost us, let's say, for example, like $4,800. Right, means that there are some fundamental differences between these switches. There are some performance differences, some CPU, RAM, resource differences on these switches, and because of that, the cost of the switches is also different. So we have to choose from these two switches. Like both the switches come with, let's say, for example, same set of ports, right? Or let's say let me add a few more ports. For example, here, let's say, for example, this switch comes with a 24 port. and this switch comes with like, let's say, for example, a 48 port, and the cost of this this particular switch is, let's say, for example, $1,000, and the cost of this switch is, let's say, for example, $3,000, something like that, some random numbers. So both the switches we can connect at the access layer. Both the switches we can connect at the access layer. Both switches have the functionalities that we need on the switches at the access layer. One switch has 24 port, one switch has 48 port, and like we have 20 users maximum. And we can go for the both of the options, like switch 1 and switch number 2. So which like switch we should go for? Like if I calculate per port cost on this switch, and if I calculate per port cost onto that switch. So let's say, for example, like there are 24 ports, and the overall switch costs like approximately $1,000. So in roughly, if I say like a single port, if I do not include anything extra, it's like a per port cost is going to be like $41. Like per port cost is going to be like $41 here. And if I go for the same here, like 3,000 divided by, let's say, for example, 48, it is going to be approximately $62. So it says that you should connect a switch on the access layer. Like first of all, we should have a lot of ports onto that particular switch, and the per port cost should be lower. Like if you have to choose between these two switches, you should go with this particular switch, because the per port cost on that particular switch is comparatively lower than this one. So that per port cost, low cost per switch port. So this low cost means like the cost in terms of money actually. Cost basically means like in terms of money. Like if we have like n number of ports, if I have like, for example, n number of ports, if I have like, for example, n number of ports on one switch, and the switch costs like, again, X amount of money. So per port cost is going to be this onto that switch, and same goes for the other one. So calculate the per port cost, and then you can decide like, okay, which switch is going to be better to be installed at the access layer. Right? Now, so you should add a switch at the access layer that has a high number of ports, and the per port cost should be lower, as lower as you can make. You should actually connect a switch at the access layer that has low cost on a like per switch port basis. Now, the switch also should have scalable uplinks to the upper layers. What do we mean by that? It means that, let's say, for example, we have this switch at the access layer, and there are 10 users connected on this particular switch, and every user can send the traffic at 100 Mbps speed. Why? Because this port is 100 Mbps port, this port is 100 Mbps port, this port is 100 Mbps port, and every port is 100 Mbps port. So every user that we have here at its full capacity, every user can send the traffic at 100 Mbps. So if this switch receives the traffic, at 100 Mbps from all the 10 ports, the total amount of traffic that it is going to receive is approximately 1 GB per second. And if the uplinks, the links going towards the upstream devices, upstream switches, if these are also, let's say, for example, 100 Mbps, the total amount of traffic cannot be successfully sent towards the upstream devices, and it might cause congestion in the network. It might cause congestion in the network. So the rate at which you are receiving the traffic is much more higher than the rate at which you are sending the traffic to the upstream devices. So that is going to cause congestion in that particular switch, on that particular switch, congestion in the network. So whatever switch you are going to connect at the access layer, it should have scalable uplinks, high-speed uplinks towards the upper layers. Like onto this switch, for example, if I have 24 ports at 10 or 100 Mbps rate, I should have at least like 2 ports that can operate in like, for example, 1 Gbps or more than that particular rate. So typically, like if I go for a simple like 2950 or 3750, 3850 series platform, if I go for 3850 series Catalyst switch platform, You can notice that on those catalyst switch platforms, we can have some extra interfaces, some extra interfaces that can be used as the uplink interfaces. For example, if I open this one, we can get like these fiber enabled uplink interfaces like that can be used to connect the switch to other switches and so on. Right? In fact, we can go for like 3750 as well. You can check on these switch platforms. So for example, here we have like these regular ports, and we have like 4 uplink ports where we can insert a gigabit Ethernet module based on fiber or based on Ethernet, and we can connect this switch with the upstream switches with the help of these 2 ports or 4 ports. So this, like this, these are what they are saying, that the switch that you are going to connect at the access layer, it should have high speed uplink ports towards the upper layer. Upper layer basically means the distribution layer. So whatever switch you are going to connect at the access layer, that switch should have scalable uplinks to the higher layers, and by higher layer, it means simply the distribution layer, or that we have the core layer. So we should have some gigabit, or we should have some 10 gig ports that we can use to connect the access layer switches with the distribution layer switches in our network. HA, high availability options. If HA options are there, then it will be much more better. And port security options are there. Port security options should be there because the end users are going to connect to that access layer switch. So we might want to bind the MAC address of that particular user with that port, or we want to add some additional security. So the port security or the additional security related features such as VLAN access list, such as DHCP snooping, dynamic RF inspection, whatever security related features you can get on these access layer switches, it will be better. HA basically high availability, like you should be able to leverage redundancy, such as in terms of power failure redundancy. So you should have for example, because remember the end users are going to be connected here. So if this switch power supply fails due to some reason, these users will not be able to access the network resources. So redundancy, high availability in terms of like switches, high availability in terms of like, for example, the power supplies and so on. So HA, if you can make the switches available for 24/7 at the access layer, it will be better. So if HA options are there on the access layer devices, it will be much more better. HA options should be there on the devices that you are going to connect at the access layer. So low cost per switch port, high port density, scalable uplinks to the upper layers such as core or distribution layer, HA options, port security, other security features such as layer 2 security features. If we can enable quality of service, then it will be better as well. So if the switch that we are going to connect at the access layer can perform basic quality of service, such as it can categorize, it can match the traffic based on certain criteria and can give some preference to that particular traffic, then it will be much better. We should not be required to add like 3 switches, one for data, one for voice, one for video. The switches that we are going to connect at the access layer should be able to converge the network services such as data, voice, and video. What is this converged network? What is this converged network? Converged network, see, in earlier days, what used to happen, that for dedicated type of traffic, we used to have dedicated link. For example, for the voice traffic, I'm going to have this link. For my data traffic, I'm going to have this link. For my audio video traffic, for example, I'm going to have, or video traffic, for example, I'm going to have this link. So in older network, in the earlier network, we used to have a dedicated link for the type of traffic, such as data traffic, such as voice traffic, such as video traffic. But nowadays, what happens? Nowadays, we follow this concept of converged network, where we do not use multiple cables, to carry the different types of traffic. In the converged network, the same cable, the same link is going to carry the traffic for data, voice, and video. So we should not be required to connect like 3 switches, one for data, one for voice, one for video, right? Based on the same. right? So that thing that we are talking about, that we should not be required. We should not be required to connect the multiple cables towards the devices, so that just so that we can forward the data traffic, just so that we can forward the voice traffic, just so that we can forward the video traffic, and so on. We should be able to connect just one cable, and the switch should be able to forward the traffic for data, voice, and video, everything out of that particular port. Right? So the switch should have the ability to converge network services such as data, voice, and video. And if we can perform quality of service for our voice or video traffic, for example, then it will be much better. So whatever switch has these property, you can purchase that switch and you can connect it at the access layer. These are recommended. The switch that you are going to connect at the access layer, they should have at least these following properties. So if you find any these properties in a particular switch, you can purchase it and you can add it at the access layer. Right? And just to tell you, we have already seen it in the last class that Catalyst 9200 series switches or 9300 series switches, they are more popular. They are very popular switches that we can connect at the access layer in a modern day campus area network. So we can consider that Catalyst 9200 or 9300 series switches, they are going to have all these properties, and they can also be managed via centralized controller called DNAC Center. Just so if later on someday we are going to migrate from the traditional to the software-defined access. So they recommend that you go for these Catalyst 92 or 9300 series switches and you connect them at the access layer. Right. Now, when it comes to connecting the access layer devices, we do not make the connection like that because it is going to add a lot of complexity. We do not do the connections like that. We do not connect the access layer switches all together like that. Typically, access layer switches are not connected together with the help of any cable or something like that. Because in that case, if I have to forward the traffic from here to here, the traffic will go all the way to all these switches, unnecessarily utilizing the cable bandwidth, unnecessarily utilizing the switch resources in middle. And as your network will grow, if you add like more number of access layer devices, and if you have connected them like this, it is going to be very complex to manage that network. So when it comes to connect the access layer devices, when it comes to connect these access layer devices, we connect these access layer devices with a new layer device, that is what we refer to as distribution layer. So distribution layer is the aggregation point for the access layer devices. So all these access layer devices are going to be connected at the distribution layer, and for the sake of redundancy, it's always recommended that you have at least 2 devices at the distribution layer. Right? So distribution layer is the aggregation point. Distribution layer is the aggregation point between the access layer devices. Like we connect all the access layer devices together with the help of the distribution layer. And this distribution layer actually provides the connection between the access layer and the core layer as well. So this distribution layer switch is actually where we draw the line between the switching and the routing. Right? Typically, at the distribution layer, we have we can either have this option where we where we perform routing at the core and where we perform switching at the access layer side from the distribution layer point of view. So the distribution layer switches that we have, this layer provides interconnection between access layer and the core layer, and the devices at this layer are called built-in distribution switches. They are responsible to aggregate multiple access layer switches together. All the access layer switches that we have, they are going to be aggregated at the distribution layer. They are going to be aggregated at the distribution layer. So if we have like n number of access layer devices, we can add 2 or 3 distribution layer devices to connect all of them together. So whatever switch we add on here, they should be very powerful switches. Because remember, This switch is sending the data at 1 Gbps from all the users. This switch is also sending the data as 1 Gbps. This switch is also sending the data as 1 Gbps. And all the access layer switches are sending the data, let's say, at 1 Gbps. Why? Because they are receiving the traffic from their end users. So this switch that we have connected here, this switch should be able to receive and process that much amount of data, and it should be able to, this switch should be able to, either route the traffic or, switch the traffic based on the parameters such as MAC address, such as IP address, from access to the core and core to the access. So that switches that we connect at the distribution layer, they must be able to handle total amount of data. They must be able to handle all the packets that they have received from the access layer, and they should be able to route it towards the core layer or switch it towards the access layer devices. So since the distribution layer is the aggregation point of multiple access layer devices, whatever switches we connect at the distribution layer, they should be powerful enough to handle all the traffic that is being received from the access layer, and it should be able to route or switch the traffic based on the same, based on either MAC address, based on either IP address. Very high layer 3 routing throughput should be available there for the packet handling. Like we should be able to perform routing based on protocols such as OSPF, routing based on protocols such as maybe BGP as well, border gateway protocol as well. The point remains the same. Whatever switches we connect at the distribution layer, routing capabilities has to be enabled there, and that switch should be able to route the packets as efficiently as possible. We should be able to run security and policy-based connectivity functions onto those switches. We should be able to run the quality of service functions on those switches, and those switches should also have high-speed link towards the core and the access layer. These links they are talking about, these links that goes towards the core layer or that goes towards the access layer. It says that these switches should have like high-speed uplinks towards the core layer and high-speed downlink towards the access layer devices. Right? So typically, like any switch that you can find with these functions, any switch that you can find with these functions, you can actually enable there. You can connect, you can add that switch to the distribution layer. You can place that switch at the distribution layer, and you can perform routing and switching based on the same. Now, access layer and distribution layer combined together is also called a switch block. So this access layer and the distribution layer combined together is also called a switch block. It is referred to as a switch block. So this is one switch block, or in fact, this, let's say like that. Just in general, this is a switch block. Switch block. How many number of distribution layer switches are going to be there in the switch block? That will be based on how many number of devices are there at the access layer, how much amount of traffic you are receiving, right? It will be dependent on like quite a few factors. Based on that, you can size this switch block. You can size this switch block based on several factors, such as how many number of switches are there at the access layer, such as how many number of switches, how much traffic we are receiving from the end users. So based on quite a few factors, we can size this switch block. The switch block is basically a combination of the access layer and the distribution layer. Right? Remember that distribution layer switches, they are going to act as the default gateway in our traditional campus area network. The distribution layer switches are going to act as the default gateway for these end users. For all these end users, these distribution layer switches are going to act as the default gateway. So for example, this user belongs to VLAN 10. We are going to create an SPI for VLAN 10 SPI, and we are going to configure it with the IP address, and that IP address will act as the default gateway on this machine. There is a user in VLAN 20. So I'm going to configure an SPI for VLAN 20. I'm going to configure it with the IP address, and that will act as the default gateway on this host machine. So these distribution layer devices act as the default gateway in our traditional network. if we have like two devices that can act as the default gateway, we can configure first hop redundancy protocol, FHRP. We can configure things such as HSRP. We can configure things such as VRRP, or we can configure things such as GLBP to perform high availability for the default gateways. So for these devices, the default distribution layer devices are going to act as the default gateway. So I am going to send all of my traffic to these distribution layer devices, and they are going to route it towards the core layer, or they are going to switch it towards the other access layer. Basically, these are the switches that perform both routing and switching. They can switch the traffic from the access layer to the access layer, and they can route the traffic from the access layer towards the distribution layer, and vice versa. Sorry, they can route the traffic from the access layer to the core layer, and vice versa. They can route the traffic from the core layer towards the, for example, access layer, and they can route the traffic from the access layer devices to the access layer devices. So they can perform both switching and they can perform routing. Now the question is how the switch will decide if it has to perform switching, or how it will decide if it has to perform routing. We'll talk about that later on, but these switches are going to perform both routing and switching. Means these interfaces I can convert as layer 3 interfaces. I can configure it with the IP address. I can run routing protocols to form the adjacencies, right? And in the LAN side, I'm going to have the VLAN connectivity. How the VLAN is going to connect with the routing network? With the help of SPI. So these switches, they are the aggregation point of the access layer devices, and these are the switches, these distribution layer switches are the points where your access layer and core layer are going to meet. So basically, this distribution layer is the point where your switching meets routing, or routing meets switching. So this is going to be called as switched access layer. Switched access layer. What do we mean by switched access layer? We mean that in between the access layer and the distribution layer, switching is taking place. And from the distribution layer to the core layer, routing is taking place. So the switched access layer basically means that here we have followed the concepts of VLAN, trunk, VTP, DTP, STP, and all. So that is going to be referred to as the switched access layer. We can also have routed access layer. What do we mean by routed access layer? We mean that all the way up to the access layer, this all is going to be routed network. Means all of them, all of these links are going to be layer 3 links. This layer 3, layer 3, layer 3, layer 3, you will perform the routing based on protocols such as EI, GRP, OSPF, and all the switches are going to be reachable to each other with the help of the IP. And since all the switches are reachable with the help of the IPs that we have configured, maybe on the loopback interface, I can manage all these switches from one centralized point called DNA center. So we can have, for example, a routed access layer where the routing is done all the way to the access layer, or we can have switched access layer. What do we mean by switched access layer? It means that we can have routing up to the distribution layer, and from the distribution to the access layer, switching is taking place. So based on your requirement, either you can go for switched access layer or routed access layer in your topology. Now, when we want to connect in a very large campus network, when we want to connect the distribution layer devices with the rest of the devices, we are going to use this core layer concept. A campus core layer network provides connectivity between all the distribution layer devices. It is also referred to as backbone sometimes, and it must be capable of switching the traffic as efficiently as possible. Very high layer 3 routing throughput should be there on the switches that you connect at the core layer. Redundancy and resilience for high availability, HA options you have to explore. We can go for things such as VSS. We can go for things such as Ether channel. We can go for things at the access layer. We can go for the things such as stacking and everything. So we should explore the options of high availability that are available at the core layer switches, and we should use those options to provide an HA network for our campus area design. So we should add some redundancy based on such as cables. We should not add only one, but let's say, for example, multiple cables. We can bundle them together with the help of the Ether channel. We can bundle the switches together with the help of technologies such as virtual switching system, VSS. Right? So we can also form this multi-chassis Ether channel in that case. A lot of options like high availability, redundancy options you have to explore, whatever options you get on the core layer devices. Advanced quality of service functions should be there. We should avoid any CPU intensive packet manipulation caused by security inspection, quality of service classification, or any other processes. So we should avoid on the core layer switches or on core layer devices, we should avoid any CPU intensive task that can utilize the CPU and that can consume CPU and lower the performance of the switches. CPU intensive tasks such as inspection, CPU intensive tasks such as ACLs or anything like that. So as long as possible, if you want to add the ACLs or quality of service or anything, then it's fine. But as long as possible, as much as possible, you should avoid adding any extra thing at the core layer devices that can consume, that can utilize the CPU and lower the performance of that particular device. Right? So whatever devices we connect at the core layer, they should have at least these following functions, at least these following options we should have on those particular devices. What options Cisco recommends, like when it comes to like adding the devices in our campus network? So what options actually Cisco recommends, like if you want to connect the devices at the access layer, core layer, whatever. So it says that if you want to connect the devices at the access layer, you should go for these platforms like 9200 series switches, 93, 9400 series catalyst switches, or 1000 series catalyst switches. They are going to be redundant power systems and all. So you can also go for these. They recommend that you go for these options when building the campus area network access layer. And when it comes to like core and distribution layer, they recommend going for 95, 96, or in the data center environment, Catalyst 7000 series switches. So this is their recommendation for the access layer and the distribution and the core layer. Based on the requirement, based on the data sheet and all, you can go for the same. Right? So fine. Okay. This is the example. So we have a few devices at the access layer connected together with the help of distribution layer. This is our building one. Right? There are few devices at the access layer, few devices at the distribution layer connected all together. This is our building 2. And we want to connect these two buildings together. Then we have to add, like, considering that it is a very big campus network, we have a core layer. We have 2 switches at the core layer, and we have added the connections from building 1 to building 2 via that core layer. So from the design point of view, 3-tier hierarchy can be represented like that. This is going to be called as switch block, and the core layer. We have a redundant core layer, means we have 2 devices at the core layer. We can have multiple links at the core layer. We can perform VSS bundling at the core layer. We can also have like VSS bundle here and here, for example, if you want. We can have the Ether channel. We can have stacking. We can have a lot of technologies in our switched campus to better utilize or better manage the switches. But from the 3-tier point of view, this is the design. This is how the design looks like. But if your campus network is not that big, let's say you only have 1 building, you do not even have the second buildings, 3rd building, 4th building. So you just have, let's say, for example, this much. So you don't need to go for 3-tier. There's no need to go for 3-tier. You can also go for 2-tier design. this is in a very large campus network. In a very large campus network, we can aggregate buildings like building 1, building 2, building 3, building 4 with multiple core layers. And this type of design is what we refer to as multi-node core. Multi-node core aggregates a very large campus area network by connecting their core layer devices. So this is, let's say, for example, a campus area network 1. This is, let's say, for example, a campus area network 2. In 2, maybe, for example, different geographical locations. Here, we had a few buildings, building 1, building 2, connected together with the help of the core layer, building 3, building 4, connected together with the help of the core layer. And now we wanted to switch the traffic from one campus area network to other campus area network. So we have decided to merge, we have decided to connect the core layers of these two, and we can handle the routing and everything. We can perform the routing in between these core layer devices, and we can route the traffic from one building to another building based on this multi-node core topology. It is for a very large campus network where we have multiple buildings, where we have multiple campuses, and we want to connect all them together with the help of the core layer. Right? So this type of design is what we refer to as multi-node core. Typically, this is required in a very large campus network, and it could be like any fiber connection, dark fiber, or any fiber connection. It could be there, like, or you can contact the service providers to provide you some sort of connectivity, or you can have your own cables from one campus to other campus, just in case if you can connect those with the help of fiber opticals or so. So you can have either, like, for example, your own cables running from one building to other building, from one campus to other campus, or you can contact the providers and they will provide you the connectivity options. Right? But if your campus network is not that big, or in fact not even that big, if you have, like, for example, this much, we have a few devices at the access layer, we want to connect these devices all together. So we have used the distribution layer, and that is it. Let's say, for example, you do not have a very big campus area network, then you can always go for two-tier design, or it is also referred to as collapsed core. The three-tier design, three-tier hierarchical design maximizes the performance, network availability, and the ability to scale the network design. So when it comes to scalability, you can go for three-tier design. But in a small enterprise network, however many small enterprise networks, they do not grow significantly larger over the time. Therefore, a two-tier hierarchical model where the core and distribution layer are collapsed into one layer is often more practical. The collapsed core is when a distribution layer and core layer functions are implemented by one single device. The primary motivation for this collapsed core design is to reduce the network cost while maintaining the most of the benefits of the three-tier hierarchical model. So it goes like this. We have, for example, a building. We have a building. We do not have that much amount of traffic to switch from one building to other building. In fact, we have a limited amount of switches at the access layer that we want to connect from one building to other building. So from the design point of view, two-tier hierarchical model can be seen like that, where we have like access layer, and the functionalities of core and distribution layers are merged together into a single device. And this layer is called core distribution layer or collapsed core. This type of model is what we are going to refer to as collapsed core model. Right? So from the design point of view, this is how the two-tier design would look like. So in our case, for example, if I do not have these devices and I connected like that, so it will be an example of two-tier design instead of three-tier design. So two-tier design or three-tier design, it is completely your choice which one you go for. Based on your requirement, either you can go for two-tier design or you can go for three-tier design. Right? So two-tier design is going to have two layers, access and core distribution, and it is also referred to as collapsed core. So from the campus area network design point of view, either you can go for two-tier or you can go for three-tier design. Now, let's say we have built our network, two-tier design, three-tier design. Let's say, for example, we have built our network, and now we want to send the traffic. So what type of traffic? How many types of traffic you can have in your campus area network? You can have a typically 3 types of traffic in your campus area network based on the flow of the traffic, you can have like 3 types of traffic in your campus area network. You have built your network, you have designed your network, you have already designed your network, like you have a few devices at the access layer, users and all. So based on, for example, the traffic flow, we can have 3 types of traffic in our campus area network. Traffic flow in the campus area network can be classified as 3 types based on where the network services are there or resources are there as compared to the end user. So this is the end user, this is the end user, and this is the resource that it wants to access. So based on the location of this resource and the end user, the traffic can be of 3 types: local, remote, or enterprise. So for example, in this topology, here we have a user. User wants to send some traffic, and if a user wants to access a certain resource, if the user and resource, exist on the same switch, they exist on the same switch, the traffic does not need to go via distribution to the core, via distribution to the other access layer devices. That type of traffic, where the traffic is switched locally from the access layer switch from the user to the resource, that type of traffic is what we are going to refer to as the local traffic. Local traffic is the traffic that originates from the, let's say, for example, user, and it goes to the same access layer device to reach out to the resources. So regardless of where the user is located, the traffic path always begins at the access layer and progresses into the distribution and perhaps into the core layer as well. Each of these layers, each layer has the attribute that provides both physical and logical functions at appropriate campus area network design. So just in case if your traffic gets originated from here, let's say, for example, there is a user that wants to access the resource, and user and resource belong to the same segment or VLAN. The services that belongs to the same segment and VLAN as the user, these services are going to be referred to as local services, and this traffic is going to be referred to as the local traffic. So all those services that we can access from the machine, and those services actually are there on the same VLAN as the user or same segment as the user at the same access layer, those type of services are we are going to refer to as local services, and this type of traffic is going to be referred to as the local traffic. Remote traffic means, for example, here is our server and here is the user. User wants to go to this server. User will go send the traffic to the access layer. From the access layer, it will go to the distribution layer, distribution to the access layer, and from the access layer, it will go to the this resource. So this traffic, when the traffic has to go from the access layer to the access layer via distribution layer, this is going to be referred to as the remote traffic. Remote traffic basically means that the user and the resource, they belong to different segment or in different VLAN. The service that belongs to a different segment or the VLAN as the user. If the user wants to access that service, the user has to send the traffic all the way from the distribution to the from the access to the distribution, and from there to access that particular service. That is going to be referred to as enterprise. That is going to be referred to as the remote service. Right? And just in case if the traffic has to cross the core, just in case there is a traffic, just in case that there is a resource, that is central, that is at a centralized location to everyone in the campus network. If you want to access that resource, you have to go from the access to the distribution to the core to the distribution to the access and then to the resource. This type of service is going to be referred to as the enterprise service, and the traffic is going to be referred to as the enterprise traffic. The traffic that crosses the core to reach out to these resources, that type of traffic is what we are going to refer to as the enterprise traffic, this enterprise service or enterprise traffic. The service that is central to all the campus users, the traffic will go from the access to the distribution to the core. That is going to be referred to as the enterprise service. So in our topology, let's say, for example, we had a few access layer devices here. They are connected with the other of 3 access layer devices, 2 distribution layer devices, and they are connected like that. So here we have a resource. We want to go from here to here. In that case, the traffic will go to the access layer, to the distribution, to the core, to the distribution, here maybe, and to the access, and then to the resource. That is what we are going to refer to as, for example, enterprise service. A service that is central to all the locations, all the users. That service is what we are going to refer to as the enterprise service. So the service that resides on the same subnet or VLAN as the user, called local service. The service that lives on a different segment or the VLAN as the user is called remote service. And if the service is central to all the campus user, if you want to reach to that particular service, or if you want to access that service, you have to send the traffic all the way from the access to the distribution to the core, and then you will be able to reach to that service. That is going to be referred to as the enterprise service. So 3 types of traffic you will typically see: local traffic, local to the access layer; remote traffic, access to the distribution; and the enterprise traffic, access to the distribution to the core. So based on the traffic flow, either the traffic can go from access to access, like from the same access layer, access to the distribution, then the access, or access, distribution, and then core, and then from there distribution and then the access. Typically, like, we have dedicated rooms for the server, so we are going to call them like server room. Those server rooms like are going to have like a lot of servers, and these servers are going to connect to the access layer switches like that, and the access layer switches are going to connect, for example, the distribution layer switches. We cannot create that much big topology. We have to it will not be able to run that much things in this simulated environment. I will try to find out a topology that represents all those things. And then I will be able to explain it based on the same. But in a typical campus network, like maybe typically like we have the servers in our data center. So in the data center network, we can follow that, the spine leaf topology and then so on. But if it comes to like if you have a small server room in your campus area network itself, so you can have, for example, servers here. These servers are going to be connected to these access layer devices here. Like this is the server. These servers are connected to the access layer devices, and these access layer devices are connected again to the distribution layer. And from the distribution layer, the connectivity goes towards the core layer, and the traffic can be routed again to reach out to these servers via the same. If you want that, like firewalls, typically we place on here, like we can place the firewalls here, and we can, define some servers in the DMZ so that those servers can be accessed via the internet services as well, outside from the internet as well. So instead of terminating the internet connection, for example, at a typical router, we can also connect it on the firewall, and from firewall we can, perform the routing and everything from the rest of the network as well. But when it comes to a typical campus, those things you will most probably cover in the security track. But when it comes to like a campus area network, typically like these 3 things you will see in a campus area network. I think like I have one topology, if I'm not wrong, I can show you that. So for example, this is one more example of the topology, like hopefully you will be able to understand it. Here, this topology is built on a packet tracer. Right, let me just show you quickly. Here, same. So this is one topology. This expands that 3 tier to from the routing point of view as well. So here we have the access layer devices going towards the end users, or we have, for example, here as the access points. These access points are going to provide the wireless connectivity to the users. We can also have the IP phones connected on the access layer, and the IP phones can go towards the end users. So the end user can send the traffic as well as the voice traffic. Both the type of traffic can be received on the switch platform, and then from there the traffic can go towards the distribution layer devices. So this is the access layer. In the access layer we have the VLANs where the end users are connected. We have the access points connected for the wireless. We have the IP phones connected so that the users can place the IP calls as well. Nowadays software-based IP phones are there that can be installed on the device itself, so that from here we can place the voice calls as well as we can send the data traffic. All these access layer devices are aggregated at the distribution layer. We have redundant links, we have redundant devices all connected together. Trunk, Ether channel link bundle, maybe VSS, stacking, just in case if you want for the management purpose. Those things you can still use. Distribution layer is the place where the routing will happen with the core layer and the switching will happen at the access layer, if you are still following the concept of switched access layer. Then from the core layer, the traffic is going to, or from the core layer, the devices are going to go towards the S distribution. Like the core layer is going to expand if you want to connect to the branches, if you want to connect to the rest of the network. So these, for example, core layer devices are going to connect the S distribution switches. These S distribution switches are going to connect us. S distribution switches are going to connect our network with the internet gateways, routers, and the WAN aggregation layer, where we are going to connect to our branches with the providers such as MPLS. So these internet gateway routers that we have here, they are responsible to actually provide us the internet connectivity. And if we have a few branches, we can also leverage things such as DMVPN to connect our campus area network with the rest of the branches using public transport such as internet. Or these S distribution layer switches, they are going towards these WAN aggregation routers. They are not responsible to provide us the internet connectivity. They are not responsible to provide us the internet connectivity. They are responsible to provide us the connectivity with the branches based on a private WAN technology, such as, for example, MPLS. Right? So, like we can use things such as L2 VPN. We can use things such as L3 VPN. Based on L2 VPN or L3 VPN, we will be able to route the traffic from one location to other location as well. Yes. The server rooms that we have, it is always recommended that you have very powerful devices connected to your server room. Like, for example, here we have 3-4 servers, and those servers are continuously in use. There are a number of users that regularly access those servers. So that the cables, the switches, the connections, redundancy, and everything should be very better onto those server rooms and all. Right? And a typical design, for example, this is just one. There is again no firewall here, because as a part of switching campus network, we generally do not include things such as firewall. But let me give you the idea. For example, like here we have the core layer devices. Instead of connecting to the internet gateways based on the router, what we could have done, we could have connected the connections. We could have added the connection to the firewall, and from the firewall we can have the internet router, and the internet router goes towards the ISPs like ISP1 and ISP2. And on this firewall, here that we have a firewall, we can have a switch. That switch is going towards a few servers in DMZ. So this is a firewall going towards a switch, and these switches have a few servers that goes towards these DMZ. So these servers can be accessed outside the campus network, from the outside the campus network as well. Right? The WLC connectivity, WLC can live anywhere. Like WLC, you can place it at the distribution layer or the core layer. All that WLC that just needs the reachability. If I have, for example, a data center, I can place the WLC in my data center, and I can make the reachability, and I can manage all these access points from that particular wireless LAN controller. In a 3-tier design, you can connect it at the distribution layer or the core layer for the better functions, or we can have these switches such as 9800 or 9300. We have some switches that have the embedded WLC functionalities. So WLC can also live on the access layer devices. So again, your choice. Reachability, you have to make sure between the WLC and the access point. There are switches that comes with embedded WLC facilities where the WLC facilities are there on the switch itself. Those switches that we connect at the access layer, they can connect to the access points and they can provide the wireless LAN controller capability itself. We can have a dedicated wireless LAN controller as well that we can connect at the distribution layer at the core layer, and we need to provide the reachability from that WLC to the access point, and that will be it. It will form the necessary tunnels and everything that is required. We can also add, like, we can also add, for example, if I have like, servers, if I have a server room, let's say this is a server room, right? These are some switches that connects to the servers and the LAN side, right? We can also add here other devices such as IPS firewalls and IPS here as well. We can also connect the devices such as firewall or IPS to the switches that goes towards the server forms, so that intrusions can be prevented and detected based on the same. So topology can be as complex as you want to. Topology, you can make it like you can add on a few firewalls, you can add on a few IPS IDS devices, you can add like a switch, connect it with the servers and place it in the DMZ so that those servers can be accessed from outside and all. So topology, you can, you can make it as complex as you want. So this is just an overview. This is just an overview how your network actually looks like. Of course, as a part of our switching content, we are not going to focus on things such as firewalls and all. So that is why I did not include any of these technologies in this one. So we can have, based on the design, based on the source and destination of the traffic, based on the source and destination of the traffic, we have, like, for example, 3 types of services, 3 types of traffic in our campus network. And I think that is pretty much it for the basics. We will talk about now the VLANs. We'll talk about the operations. We'll talk about the functions of the switch. What are the functions of the switch? How switch operates? What is address learning? What is filter forwarding decision, MAC table, CAM table, and everything? We will talk about all that from tomorrow. But from the design point of view, how the design is going to be there, where the routing is going to take place, where the switching is going to take place, what is SPI, what is CDP, what is LLDP, all those basic things are actually done.